Okay, hello everybody. Great, I hope you are doing well. Just to check, do you hear me in both rooms? Hi, Shant.
Hi, Nima. So I have your voice in the second room.
Good. Good, thank you. And okay, here we go. So the first, there is one announcement, very quick announcement, is that as you may, as we mentioned on the website, the Starkman talk is a little bit earlier, so it will be on the first session of the second, the first part of the second session today. Today we have many contributed talks in two different rooms. One of them is in the main room, and the other one is in the room number 2. And in the main room, you can see in chat box that there is the address for the room number 2. And what should I say more? Oh, okay. Subir had a follow-up on the discussion he had with Mike Hudson, and he posted some, you can see in the chat box of the main room, he posted some comments on that. Okay, great. So we will start in 2-3 minutes. Before that, I can say in Iran, it is Father's Day, so happy Father's Day to all of you. And I don't know, is there anything more? I don't know, Puyan, Shant, Marzieh. No, I think there is. Oh, sorry, Shant. Sorry, my.
So we are okay. So we are. Thank you.
Please. I didn't hear you, Shant. My speaker was off. Okay. So we can start. I mean, in 2 minutes we will start. The chair for this session is Shahab, and for the room number 2, it's Shant. So it's on you.
So great. So hello everyone.
Shahab, we cannot hear you.
If you go to the second button on the right, it will be okay as well. Yes.
Puyan, can you help Shahab? If Shahab, do you use Chrome?
Yeah, what's the problem? Can you please, yeah, if you cannot speak, write in the chat box what's the problem?
So hopefully I'm sharing my screen now.
Yes. If you go to the share screen mode,
Am I sharing the screen?
so we have your slides, but they're
Shahab, yes. Can you raise your hand, please?
Okay, you should have the
Okay.
microphone now.
Do you hear me?
Yes, please go ahead.
Okay. Thank you. Just for check, do you see my webcam and hear me again?
Yes.
Okay. I think we should start. Hello, everyone. Good evening here, and good morning and good night, I think, from other places. This is the first parallel section of the last day of this very interesting conference. I would like to thank the organizers, especially Nima, for very hard work. I think we should start. Our first speaker is Ryan Keeleey. He sent us a video of his talk, and he will talk about inflation wars, a new hope. Let's see his talk, please.
Hello, everyone listening in the future. I am Ryan Keeleey, a postdoc with the Cosmology group at the Korea Astronomy Space Science Institute. I would like to thank the organizers for the opportunity to give this talk and all of you for your attention. Today, I'm going to be telling you about some ways to use model-independent methods in cosmology, particularly about how to reconstruct the primordial power spectrum from CMB observations. The reason we want to do this reconstruction is because we want to test ΛCDM in novel ways. We want to pull on the model in various ways to see if it holds together or falls apart. And since ΛCDM has increasingly emerged as a concordance model of cosmology, it has become important to test it in increasingly novel ways. ΛCDM explains a number of datasets well, at least individually. In broad strokes, the ΛCDM model explains well the anisotropies in the cosmic microwave background, how those anisotropies cluster and grow into the observed large-scale structure of the universe, and how the expansion of the universe accelerates at late times. However, there have emerged a number of tensions between the ΛCDM parameters inferred by different datasets. Most notably is the so-called H0 tension, which is a 4.4 sigma discrepancy between the present-day expansion rate directly observed from the Cepheid anchoring of the supernova distances and that rate inferred from the Planck measurements of the cosmic microwave background. Other low redshift distances and anchors, such as strong lens time delay distances and the tip of the red giant branch, also display some tension. There are a number of other tensions involving the growth of structure and other ΛCDM parameters, such as the curvature or matter density. Taken together, these may point towards a discrepancy between high and low redshift physics. While there have emerged a number of explanations that have reconciled the Planck temperature dataset and the Shoes Cepheid dataset, most have not been able to jointly explain every cosmological dataset simultaneously. Notably, explanations that modify the physics at or before recombination tend to fail explaining the polarization datasets or the large-scale structure, while explanations that introduce new physics at low redshift tend to fail explaining either the BAO distances or supernova distances. So rather than iterate through a possibly infinite number of nested extensions to ΛCDM, even in a hierarchical fashion, or even yet discrete alternative models, it can be more fruitful to use model-independent methods to search for a satisfying explanation to the H0 tension. It is in this context that we have to be as agnostic as possible. Our statistical methodology has to be flexible enough to allow for surprises, to allow for unknown unknowns, and thus we must use model-independent or data-driven techniques. For cosmology, it is better to use data-driven techniques to reconstruct the distance redshift relationship from the data directly. With the reconstructions, one can then build a model around what the data are trying to say. As Sherlock Holmes would say, it is a capital mistake to theorize before one has data. Insensibly, one begins to twist facts to suit theories instead of theories to suit facts. Specifically, in one recent work, collaborators and I have used the modified Richardson-Lucy algorithm to reconstruct the primordial power spectrum from the Planck CMB data. The primordial power spectrum is important because it, above all other cosmological observables, contains information about inflationary physics. So if we are able to reconstruct a novel primordial power spectrum, that would indicate novel inflationary physics. So the idea with this reconstruction is we want to see if we can reconstruct a novel primordial power spectrum that would satisfy both the Planck CMB data as well as the low redshift expansion history, i.e. to reconstruct another solution to the H0 tension. A power law primordial power spectrum corresponds to single field slow roll inflation with nearly scale invariant spectrum, and a non-power law primordial power spectrum would infer much stranger inflationary physics with potentially steps or kinks in the potential or large field inflation. So in general, the observed angular power spectrum of the CMB is a convolution of the radiative transfer kernel, or the transfer function, which incorporates all the information about the background expansion history and with the primordial power spectrum. So we use a radiative transfer kernel with a background expansion history consistent with the lower redshift distances, i.e. H0 from shoes, omega matter from kids and supernova, and then with this radiative transfer function in hand, we can then use the modified Richardson-Lucy algorithm to iteratively find the primordial power spectrum that net yields the same CLs as specified Planck power law. To explain a bit more about how the modified Richardson-Lucy algorithm works, I present this slide. So to explain some of the symbols, here G tilde is a transport kernel, the CLD is the data, the CLT is the theoretical angular power spectrum corresponding to the primordial power spectrum at some ith iteration of this algorithm. It is important to emphasize that this modified Richardson-Lucy algorithm is an iterative process and ensures the positivity of the recovered P of K, basically since GL is a positive definite matrix. And further modifications include this tense term, which is used to account for uncertainties in the data and to make modifications where the data and the iterative recovered theory CLs are the most different. To understand the effect of this primordial power spectrum and why it yields a high value for the Hubble parameter, we must first understand what effects changing the Hubble parameter would have when fixing the primordial power spectrum to the best fit power law. So just shifting H0 induces a purely geometric modification to the CMB's CLs by changing the inferred angular diameter distance to the surface of glass scattering. This in turn generates a phase shift in the CLs that is consistent across acoustic peaks. So in effect, the MRL deconvolution is undoing this change, the change caused by shifting H0, and it generates a primordial power spectrum that de-phase shifts the CLs. So in fact, the MRL reconstruction accounts for the different geometry with power spectrum features. The effect relative to the best fit ΛCDM of changing H0, changing the primordial power spectrum, and changing both are shown here. The figure shows the CLs for a power law, ΛCDM model with H0 of 73, a modified Richardson-Lucy reconstruction with H0 equals 67, and a modified Richardson-Lucy reconstruction with H0 equals 73.5, all relative to the best fit power law ΛCDM model with H0 of 67.8. The two different modifications induce basically equal and opposite changes to the CLs, which when combined induce basically no change. So since the reconstruction itself is basically only exploring 2 points in a parameter space, we want to generalize these results as far as possible. And so to do this generalization, we take the reconstructed power spectrum and basically use it as a template. We can then interpolate between this MRL template and the best fit power law, while varying the background parameters as well. So when we do this, we essentially have the same 6 parameters as the base ΛCDM model with one additional parameter f, which characterizes the deviation towards the MRL template primordial power spectrum. I refer to this thing as a whole as the deformation model. So in the figure here, we simply display a few instances of the deformed MRL-derived primordial power spectrum, where f equals 0, corresponding to the blue in the figure, is the MRL PPS, and f equals 1 is the yellow, which corresponds to the best fit Planck power law primordial power spectrum. So with a model in hand, we can then do typical Bayesian analysis, where we first calculate the posteriors for the parameters of the deformation model using only the TT dataset from Planck. This is to show that independent of the Cepheid H0 measurement, the deformation model can predict H0 values higher than ΛCDM. Then when the Cepheid H0 constraint is included, we show that the resulting parameter space is actually a good fit to both datasets simultaneously, and thus resolving the tension. So in this figure, we show that the results for the deformation model, for the TT dataset alone, the best fit parameters of the deformation model are H0 is equal to 70 plus or minus 1.2, and F is equal to 0.64 plus or minus 0.2. The best fit parameters yield a likelihood better than the best fit ΛCDM model with a delta log likelihood of around 2.5. This is intriguing since even on its own, the deformation can explain the temperature anisotropies in the CMB better than the ΛCDM model, while also predicting high values for H0. So we calculate a Bayes factor for the two models where k is equal to the ratio of the two evidence. So k z over z. So where k is equal to z deform over z ΛCDM, we get basically a log k value of 2.2, which is relatively marginal evidence. But then when we do combine the Planck dataset with the Cepheid H0 measurement from Rees et al., the best fit parameter shift is 70. H0 is equal to 72 plus or minus 0.9, and f is equal to 0.4 plus or minus 0.16. And basically the ΛCDM regime, f is equal to 1, is strongly ruled out. Further, we find the Bayes factor to be a log of k of 5.7, which according to the Jeffrey scales amounts to strong evidence. So now we seek to answer the question, which features in the MRL reconstructed primordial power spectrum are primarily driving the preference for parameter values that are different from those inferred from the ΛCDM? One potential way to answer this question is to apply various smoothings, filterings, or wavelet transfers to the MRL reconstructed primordial power spectrum and check if the resulting primordial power spectrum can achieve the same likelihood. So even simple techniques like frequency cuts and low-pass filters suppress the features in the range k is around 10 to the -4 to 10 to the -2, leaving only the sinusoidal oscillations at high wave number. To test the effect of the filter, we scan over the cutoff frequency of the low-pass filter and calculate how much the likelihood changed. For larger values of the cutoff frequency, the change in the PPS in the primordial power spectrum is smaller. When scanning over the cutoff frequency, we found no preference for any filtering, but some amount was still allowed. So applying a cutoff frequency of 0.6 megaparsecs to the MRL primordial power spectrum, the likelihood is marginally worse, with around a delta log likelihood of 0.5, but the jackiness in the high wave number part of the MRL primordial power spectrum is removed. So the cost and the likelihood buys us a priori subjective belief. Further, all of the high frequency features are removed. To more precisely answer the question of which features give rise to the MRL preference for a high H0, we also tested a case where the low pass filter was applied to only the features above k greater than 0.25. This choice was motivated by the fact that above 0.25, the only meaningful effect of the CLs is for L values of greater than 2500, so which is a regime that is basically unprobed by Planck CMB observations. Keeping with these expectations, we find that essentially all of the features above k of 0.225 can be filtered away and maintain the same likelihood. We showed this high k filtering case in the figure here, where in green we show the filtered part of the primordial power spectrum. The blue is the MRL, and the green filtered curves combined form the tested primordial power spectrum. Thus, it is apparent that these mid wave numbers between 0.01 K values between 0.01 and 0.25, these oscillations are what compensate for the phase shift in the acoustic peaks coming from the different background parameters. So it's not unreasonable that these features could arise from steps or kinks in a physical inflationary potential, such as wiggly whipped inflation or something similar, and thus these sort of deformed or filtered primordial power spectrum models offer a new hope that inflationary physics beyond the simplest single field.
Okay, thank you, Ryan. I think we have Ryan here. Ryan, could you please turn on your Hi. Hello. Thank you very much for your very interesting talk with very interesting title, I think, because it resembles the Star Wars. Okay, we have time for some questions. If anybody have any question, please raise your hand, and we can turn on your microphone. Okay. May I ask a very simple question? You talk about H0 tension, but I don't see you mention about sigma 8 tension. Is it? Does it have something to do for that tension?
Not explicitly. So probably the most likely place where this kind of model would have specific predictions for other kinds of tensions is with the sort of a lens anomaly. Basically, because that's purely coming from, I guess, supposed to be coming from different, basically mismatches between different parts of the Planck CL inferences. So I mean, So basically, this shouldn't predict any specific difference in the in essentially the amount of clustering. So it doesn't have anything specifically to say about sigma 8.
Okay, thank you very much. Let's thank Ryan again, and I think we could go on to the other type. Thank you very much, Ryan. You could stop your video. Okay, our next talk by Hanwool Koo from COSI, and he will talk about cosmology with type 1A supernovae, searching for systematics and model-independent reconstructions. Okay, he also sent us a video. Let's see his talk. Thank you.
I wish to thank organizers for giving me a chance to present our recent works. My name is Hanwool Koo, and I'll talk about our 3 recent papers with the title of Cosmology with Type 1A Supernovae, Searching for Systematics and Model-Independent Reconstructions. For more detail, please see the 3 papers on the slide. First, I'll give a brief introduction about the studies. Type 1A supernovae, SNE1A, are used as standardizable candles for distance measurement and have become one of important portion of modern cosmology. However, the standardization is purely parameters and hyperparameters. The light curve hyperparameters are usually constrained based on assumption of cosmological model, but we can find the model-independent manner to constrain the hyperparameters. In addition, to search for systematics in the SNE1A data, model-independent reconstruction is required. After reconstruction, we can look for features in the data which can be a hint for systematics or new physics. We can also perform model selection and parameter estimation without comparing models. To do all of this, we apply the iterative smoothing method, which is the non-parametric method to reconstruct the distance modulus and expansion history of the universe. It is introduced by Sheffield et al. In 2006 and improved by following papers on the slide. This method starts from initial guess of distance modulus, but generates model-independent reconstructions of distance modulus with lower chi-square value after numerous iterations. We can find equations for each iteration on bottom of the slide, and more detail in the paper. Next, to construct the distance modulus from the data and use them for constraining the light curve hyperparameters, we use the joint light curve analysis, in short JLA compilation, which have light curve parameters information based on sawtooth fitting model, and apply the 3 formula. Among the parameters on the formula, 2 proportional factors, and 2 absolute B-band peak magnitude parameters. Are light curve hyperparameters that need to be constrained, while others are light curve parameters provided by JLA. We assume 3 different cosmological models with 3 different colors to compare their hyperparameter constraints with those from the reconstructed distance modular, like colored in red. As we can see on the right corner plot, contours are all consistent with each other, which indicates there is no dependence on cosmological model. One exception is that large MB1 from reconstructions shows uniform distribution because SNE1A alone cannot constrain an absolute distance scale. Next, we divide the data into 2 redshift bins with equal size and compare the constraints from the constructed distance moduli. We can see that statistical deviations between the 2 contours are not large enough, which indicates that there is no clear redshift evolution. From now on, we talk about looking for features in SNE1A data using the more recent Pantheon data. We find oscillating features in the Pantheon data at redshift lower than 0.5 around the best fit ΛCDM model. We have tried to see how generic such behavior is found at many Monte Carlo realizations of the data, using full covariance metrics of the Pantheon data. The 2 circles on this table shows that the deviations of the redshift bin best fit parameter values from their full dataset best fit values are larger than or comparable to 1 sigma, which indicate oscillating features. Such features occur in 4 to 5% of Pantheon-like simulations. We think that it might be a hint to possible systematic or new physics. Finally, we talk about direct model testing. We do this because model testing using Bayesian evidence depends on comparing models. We try to test consistency of a model and the data without comparing different models. By estimating likelihood distribution of delta chi-square using iterative smoothing method for model selection and parameter estimation. For model selection, we define delta chi-square as chi-square difference between smoothed reconstruction and model best fit initial guess. Remember that the iterative smoothing method starts from initial guess. We can see that likely distributions of delta chi-square for 3 different model best fits using 1000 Pantheon-like mock realizations based on 3 different fiducian models are the same with each other, which indicates no dependence on cosmological models that are used for simulation. And for parameter estimation, we use the fiducian models as initial guess for defining delta chi-square. In this figure on the slide, we can find that the likely distributions are the same with each other, which indicates no dependence on cosmological model again. This figure shows estimated constraints on matter density at present time for 3 different models using 95% confidence limits for Pantheon. We can see that they are highly distinguishable with one another. Next, we perform model selection with future data, which is 1000 forecasted W1st mock realizations based on ΛCDM fiducian model. Note that the official name of W1st has changed to Nancy Grace Roman Space Telescope. As shown on figure and table on the slide, the likely distributions for the 3 different models and their estimated type 2 errors beyond 95% or 99% confidence limits are highly distinguishable from one another. Now, here I summarize that we find no model dependence nor redshift evolution of light curve hyperparameters. We also find that 4 to 5% of Pantheon-like simulations have similar oscillatory features with that in the Pantheon data, which might indicate systematics or new physics. Finally, we show that model selection and parameter estimation using the iterative smoothing method works well, which might confront with Bayesian analysis in the future. Thank you for listening to our talk and comments. comments are always welcome. And for more detail, please see the papers on the slide. And for more detail, please see the papers on the slide.
Okay, thank you. Okay, thank you very much, Hanwool. I think he is with us. Hi, Hanwool. Very nice talk. I would like to thank you again. So, if anybody has questions, please raise your hand. Okay, we have, I think, 5 minutes before we could start the other talk, so we can discuss about this very nice talk. Okay, I think I should start questions. Would you please tell me why you do you split the redshift range into two ranges? Why two?
Because we tried to check the redshift dependence. So that's why I performed the binning. So maybe so you asked this question because why the number of the bins should be 2?
Ah, yes.
Okay. Okay. Well, so first of all, I tried to divide the redshift, set the number of bins into 3, and try to make them have the equal number of type 1 supernova, which result in very different size of the bin. So I find that which happened because the most of the type 1 supernova are concentrated in the on the low redshift. So I have another. So I choose to divide them into the redshift bin with equal size rather than equal number of type 1 supernova. Then I find that divide them into 3 redshift bins with equal size. If I divide them into 3 equal size of the bin, then the third bin includes 2 low number of type 1 supernovas. Simply that's the simple reason that I choose 2 redshift bins rather than 3 redshift bins or more than that.
Okay, thank you very much. I think nobody has any questions. Thank you. Let's thank Hanwool again. Okay, we can start our third talk by Lan Nguyen, if I spell it correctly. Lan, do you hear us?
I can hear you very well.
Okay. If you want, you could turn on your webcam.
Yes.
Okay. Hello. Nice to meet you virtually, and we are very happy to have you here in Tehran again virtually. Okay. I think you have a PDF file. Would you please upload it?
Oh, so should I share screen or?
Yeah, the file is uploaded. Just go to the Files option on top right of your screen.
Okay.
And you will see your file here.
Okay. Thank you, Tia. Okay. Let's start with talk by Professor Lan Nguyen. She will talk about self-interacting dark matter and small-scale structure problems. Okay, let's go. Thank you.
Hi everyone. My name is Lan Nguyen. So Right now, I'm at the University of Notre Dame, and today my talk is about the self-inducting dark matter and the small scale structure problem. So, when we look into the, at first, I'm working on the model for the self-inducting dark matter. So the reason I'm interested on this because when you look into the large scale structure, there's a mid mid misconception between the simulation and observation. So the self-inducting dark matter could be a candidate for solving problem on the smaller scale structure. So at first, I look into the model for the dark matter. So we work on the when we look into the standard model, there is no candidate for the dark matter. So we have to look into the beyond standard model. So in the beyond standard model, we look into it's called a 331 model. So in this model, we don't see that we look into the Yukawa interaction, and there is interaction between the dark matter and Higgs boson, and it doesn't interact with any ordinary dark particle of the standard model. So we found that there are two candidates for the dark matter, and one is a boson and the other Prager boson. So which is the candidate for the dark matter, we use Boltzmann equation you can see here, and the mechanism for the dark matter in that model is it's called the thermal average of the decaying rate. And with all of that, we calculate the cosmic density of the scalar particle, and we found that it's in this formula omega here. So with all of that, we apply with the mean free path is in the range from the 1 kiloparsec, and it's less than a lot with the megaparsec. And self-inducting dark matter candidates would have density, number density, and have density is density at the solar radius, and we calculate the mass for the particle is in the range from the 4.7 MeV to 29 MeV, and density is omega 8 is in the range 0.14 to 0.3, and this is a cross section over mass in the range from 2 times 10 to minus 10 to 3 until 2.57 times 10 to 10 to 4. So which is the cross section we try to apply to constrain it to the galaxy simulation and the cosmic microwave background. So the issue is come up here. So you can see that is with a different experimental observation like the cosmic microwave background, cluster abundance, and galaxy clustering and gravitational lensing. So with all of these observations, we see that it's a very vast fit between the theoretical prediction and observation in the range from the 100 light year to 10,000 million light of light year. And so, but in the smaller scale, like the less than, you can see here it's less than 100. It doesn't fit very well between the theoretical and observation. So that is the problem with the smaller scale structure. So smaller scale structure is here. It can be we can look at the dwarf galaxies. So. And you can see like in the different galaxies, like in the Ultra Minor and Draco and Keeleey and so on. So you can see that is in the L is less than 10. So it doesn't fit here. So as you can see, the black line is a theoretical prediction, and the other is from observation. So the question is raised here is dark matter interaction have a contribution on all of this. So, and you can see in this figure, it's like the blue line is for self-inducting dark matter, and the dot that line is for cold dark matter. So for the self-inducting dark matter in the radius less than 5 kiloparsec is kind of more fit to the theoretical. So the way you working here is we look into the self-inducting dark matter. It's a beyond standard model, and you can see that it's a dark matter in this case have a cross section is long and collisionate and thermalization. So in this way, we want to look into the smaller scale structure for 3 problems like the 2 big tooth files, missing galaxy satellite, and Concordance problem. So we work in the first problem is a Concordance problem, and the other thing the other problem that we think that how inducting dark matter can be solved is the missing galaxy satellite. So for the missing galaxy satellite, it will constrain with the gravitational lensing. But for the Concordance problem, we will look into the galaxy simulation and cosmic microwave background. So we can see here in the red one is a cold dark matter for the cold dark matter, and the blue one is for observation. So the gray is a structure formation in the self-inducting dark matter universe is it started from the early universe, and then hollow masses, and then have appears a self-inducting dark matter with the mechanism is it's called the heat flux, and it going to explain for the galaxies formation and evolution includes gas and stellar physics. So is simulation for the galaxies. So you can see here is for different model, like for the cross section, with the cross section of the cold dark matter is nearly 0, and in the previous calculation, like Annika coupling hat and Hofer, they already consider with a cross section in the range from 0.1 until 3. So in our model, when we have a cross section over mass is in the range here, and we convert it into the cross section unit of the centimeter square over g. So it's range from the 4 to 5. It's exactly is from 3.7 until 5.3. And we run for the gaseous course and to see that the remote simulation for the self-inducting dark matter is more flat out compared with the cold dark matter. And the other constraint we did is we compare we constrain with the cosmic microwave background, and you can see that it's in the smaller scale is the cold dark matter and self-inducting dark matter. Self-inducting dark matter is kind of slow down compared with the cold dark matter, and in the range L less than 100. So so in this one, in this case, that only solve for the cost problem, and we expect that we can do for the missing satellite, but we don't think that is a self-inducting dark matter in our model could be constrained for the too big to fail problem. And the other direction we want to work in the candidate for the dark matter in our model is we look into the mechanism that forming the dark matter in the in the supernovae collapse. So dark matter could be forming during just supernovae collapse and forming the dark matter halo around this the neutron star. And when neutron star merge together, it could be have a imprint of the dark matter in the gravitational wave signal from the binary neutron star merger. So so far, I think that it's a self-inducting dark matter is a well-motivated dark matter theory that can explain for the problem of the cold dark matter on smaller scalar structure. So that is all for my talk. Thank you for thank you. Yeah.
Okay, thank you very much. Let's thank Lan again. Okay, we have time for a couple of questions. If you have any question, please. Okay, this it seems that your talk is perfect and nobody have any questions. That's great. Okay, if nobody has any question, okay. Thank you very much again for very interesting talk, and I hope that we can see you personally here. Okay. The first part of this contributed talk is finished, but let's start the second part with okay. This talk is by Joachim Harnois-Déraps. Okay, Joachim, do you hear us?
Yes, I'm here.
Okay. Okay, nice to meet you, and welcome virtually to Tehran. Okay, would you please select your PDF file from? Okay, thank you. Okay. Joachim will be talk about dark energy from cosmic shear beyond power spectrum. Okay, Joachim, go ahead, please.
Thank you. Can you all hear me well?
Yeah, of
okay,
course.
Perfect. So I'm very pleased to be presenting today. It's also nice that some people have introduced the basics of cosmology and wave lensing. So we had fabulous talks by Marika Asghari and Alex Amon that introduced the data, KiDS1000 and the dark energy survey. This talk is about how can we extract more information from the same data. And it is really important to think about that because the next generation of galaxy surveys are really costing billions of euros and billions of dollars. Some things like the Rubin Observatory or the Euclid flying telescopes. And so it would be a shame to throw away half of the information just because we are looking only at power spectrum. So what I want to present here is methods to extract motivation and methods to extract information beyond the power spectrum, or in general the two-point correlation functions. So as presented in this talk, in the title of this talk, it's mostly focusing on cosmic shear, but there are applications beyond cosmic shear. Why we want to go beyond, the first questions we want to answer. So if we look at these two panels, this is a clear example of two matter density, which are projected along the line of sight. And they have the exact same matter power spectrum. So if you compute the two-point statistics from these two panels, you have exactly the same answer. However, one has filaments and clusters and voids, and the other is only just Gaussian noise. And that's basically, it's telling us that there is information contained in the filament in the nonlinear clustering that is not recovered by the power spectrum. And the goal here is to try to recover that information that is stored in the phases. And we achieve this by looking at non-Gaussian statistics, so going beyond the power spectrum. So the main approach I've been using is to use weak lensing numerical simulations. And the reason is that we do not always have a good model, a good theory, if we want to measure cosmic shear measurements. If it's not power spectrum, then we need to model whatever we're measuring. So I've been spending a lot of years making light cone simulations that then look like the weak lensing data. So in particular, one needs to have a suite of simulations in which the cosmology is varied, so you can calibrate your signal and find the best fitting model. You also need a second suite to evaluate how your data elements are correlated with one another. So the covariance matrix is one of the key ingredients in these analyses, and it's something which is very expensive to produce because we need suites of simulations. So in any case, it all starts out with running suites of n-body simulations tailored to construct past light cones. And then these light cones are then shaped into a survey. So in this case here, I've been using a Euclid-like survey. So the galaxy distribution follows one of the forecasts for Euclid. And then this little panel here is showing the points in cosmological parameters for which I do have a model. So there are 26 points, and then this is a WCDM, so the dark energy equation of state is allowed to vary away from -1. I'm also varying S8, which is one of the parameters that's best measured by weak lensing data, and also the Hubble constant and the matter density. Now Hubble does not really, the weak lensing is not very sensitive to H, but since there is a tension, it's nice to have that parameter being able to be varied. And the cross here in these little panels is a point where I do have 900 fully independent simulations for which I can evaluate the covariance matrix. And with the signal in the covariance matrix, I can then run a likelihood analysis and make a forecast or a measurement. So basically, from observations, which are pictures, the first step is to derive catalogs. So I'm not doing a catalog. Some people are much better than me go from pictures to catalogs. So Ben Giblin in the audience here has been doing this very great work for the kilodegree survey. And out of these catalogs are ellipticities and positions. So this is a thing which you can examine. So in the standard method, where we look at two-point correlation functions, the standard method uses the shear, the ellipticity, ellipticity 1 and 2, and the positions, and measures something like the shear two-point correlation functions, which is shown here in the top panel. And then once we have the redshift estimate of these populations, we can also feed that into theoretical predictions, which are written in small in the bottom right corner of this slide. And when we combine everything together, we can make a cosmological inference and make a measurement of cosmological parameters. The big difference, if we steer away from the two-point measures, is that we no longer have good theoretical predictions. So instead, we use n-body simulations that look like your model. And then instead of measuring two-point correlation functions, you measure something like features in a lensing map. So the top panel here is showing one of these reconstructed mass map from mock cosmic shear data. And we can see in gray, in blue, and in red underdensities and overdensities. And then the thing is that you can then examine these maps and ask new questions. So maybe counting the clusters, counting the voids, looking at void profiles. So these are all different kinds of analysis you can run on these maps instead of looking at the power spectrum, and then combine that with the simulations in the data and make your forecast or your measurement. So when we do this, I should quickly touch on a subtle aspect, which is tomography. So tomography is basically interested in looking at the redshift evolution of your signal. So in the past, up to last year, when people looked at tomography beyond power spectrum, they would slice their data or their simulations in different redshift bins. And then for each of these bins, you could construct a map like these ones, which are labeled Z1, 2, 3, and 4, and 5. So these are all maps that are reconstructed in separate redshift bins. Then you can also, if you want, combine them all and do node tomography, where you just collect, make your map from all the data together, and then run your statistics in each of these maps individually. However, there's some part of the information which is missing, is that if you count the objects, say in Z1, 2, 3, and 4, you don't know if these are lying across the redshift, because you're just counting objects. You don't know if physically they are the same locations. But a big cluster will have a signal in all of these bins, and this is shown in the Z-all. Like you have this big red blob which has a contribution in at least Z2, 3, 4, and 5. If you just count objects in Z2, 3, 4, 5, you don't recover the big cluster. You're missing this information. So we have been developing a new method here where, in addition to looking at these individual redshift tomographic bins, we also combined the catalogs of 2, 3, or 4 of these bins, and then make these maps. And then we recover in the bottom row new panels in which the signal progressively emerges. So that contains new information as well. So this is one of the things that I think everybody needs to start doing if you want to optimize your analysis strategies. So what's the gain in terms of dark matter and dark energy? We have been looking at these Euclid-like survey, and it turns out it's pretty impressive. For 100 square degrees of Euclid, if we do a 5-slice tomographic binning, you can improve the constraint on S8 by a factor of 2. This was known, but on the measurement of the dark energy equation of state, that improvement is by a factor of 3. So this was never done before. And it was pretty surprising to see that the dark energy is so sensitive to the peak counts. So it just tells us that small changes in the amount of dark energy have very big consequences on the amount of structure that emerges in these maps. And so this sensitivity is larger than for two-point correlation function. And it just means that there's a lot of nonlinear structure that grows out of small perturbation in dark energy equation of states. So this is very beautiful. We have a nice forecast, a very strong motivation. We want now to start to look at this in the data. We do not have the Euclid data. We have instead stage 3 weak lensing survey. So I'm going to be talking about recent analysis I've been doing on the dark energy survey year 1 data, which is public. So this is the link where you can look in more detail on this analysis. But when you go away from simulations and start to look at data, this little mantra here is very important. In theory, in practice are not the same, but in practice they are not. So that means just basically in my case, it means that when you look at data, there's a load of different systematic effects and observational effects that are not part of your theory at first, and you need to include. Everything is more complicated, but that's the beauty of it. So here, what I'm showing here on the left panel is the position of the dark energy year 1 data. So every little black point is one galaxy. There is 25 million galaxies that are used in this analysis. But the survey footprint of the data is larger than my simulated light cones. So the simulation light cones are 100 square degrees each, which means that I need to tile the survey in a kind of a mosaic. So each of these red squares is one of the light cones, and I've been tiling the data with the simulations. The simulation suites that I've been using, so one of them is varying in cosmology, it's called a Cosmology. The other one varies the initial conditions. So I have 900 of these, which means that I'm probing the sampling variance to have an accurate error bar on top of just the mean. I'm also using different simulations to look at the impact of mass resolution from these simulations, or the impact of baryonic feedback. So the Magneticum 2 and 2B simulations do have baryons and AGNs and supernovae feedback in them. And I've been running my analysis on these as well, and looking what's the effect of baryons to be protected against them. I'm varying the parameters omega m, S8, H, and W0. It turns out that the current data only is only able to constrain S8 well. The others are hitting the prior boundaries, so I cannot really tell anymore. What I've been looking at is, for this exercise, is a peak count analysis. So from the the convergence map I've been reproducing, I was counting peaks and binning them as a function of the height. So it's a peak mass function that I've been measuring. If you have only random noise in your data, random noise will have peaks as well. So this plot here shows the difference between your measurement in the cosmology signal and between the pure noise analysis. So n peaks minus n noise have this shape here. The x-axis in this panel is the strength of the signal to noise, so going from 0 to 4 in each of these panels, and then the y-axis is the relative difference. The points here are from the data. The error bars is estimated from my 900 simulations, and all the colored lines, the histograms, are basically variation as a function of cosmology, which are color-coded by values of S8. So magenta lines are closer to the origin, they have lower S8, less clumpiness, so they're closer, I guess they're closer to noise, whereas the blue lines have a load of clusterings, so there's stronger deviation. So basically in this analysis, I have been using the exact position and the exact absolute shape noise of the data, but the shear, the cosmic shear, was extracted from the simulation only. And then having only 26 simulations in which the cosmology is varied, I had to interpolate in between to run an MCMC afterwards. And I used the Gaussian process regression emulator. And I will show in a few slides that this introduces a negligible error. So the interpolation error is extremely small. So the systematics now, this research here is really focusing on trying to nail down systematics at the same level as what's done explicitly for two-point collision function. So this is the list of systematics I've been investigating. The interpolation error, when we have only a finite number of nodes to estimate the signal, photometric redshift uncertainty, the shear calibration bias, the mass resolution of the simulations, baryonic feedback, the intrinsic element of galaxies, the mosaic tiling method, using a simulation-based covariance matrix, and also the inference pipeline. So I've been testing all of them, and I don't have time to go through all of them, but I can maybe just show you the simulation pipeline here. I'm going to be showing this one here. So this is basically looking at the difference between the two-point collision function measurement from my simulation and the peak simulation, the peak analysis, the peak count analysis from the same simulation. So the data here is not the real data, it's a simulation, but in which we know the cosmology. And if you look at the difference, so the blue contours are from the peak count analysis, whereas the gray contours are from the two-point collision function analysis. And they recover perfectly well the input cosmology of the simulations in all of these panels. And the red contour is the constraints from the Troxel et al. So that's the data analysis that's been done by the dark energy survey. So basically, these all align pretty well. So it validates the full pipeline. And this is after marginalizing over many of the systematics. When I unblind and look at the data, I recover something a bit different. So the blue, again, is the peaks, and the gray is the two-point collision function. And in the data, there seems to be this shift, whereas the peaks and the two-point collision function agree very well in S8, but not so well in omega m. And so one of the big questions we've been asking is, what's happening here? So we spent a couple of months trying to figure this out. And it turns out, if we look at simulated data, and in these light cones, you can measure two-point collision function, you can measure the peaks, and ask, if you do a cosmological inference on these two measurements from the same simulation, do you recover the exact omega m, or do you have does it happen that sometimes the same data prefers two different values? So we've run that 50 times, 50 light cones, in which we've measured two-point collision function peaks, have asked for the best recovered value of omega m and S sigma 8. And this is showing in the red panel here. The red panel is showing the results in the orange square. That's the best fit inferred cosmology from the two-point collision functions. And in blue is the best fit from the peaks. And each result from the same simulation has been linked by a straight line, basically. So some of these straight lines are short, which means that the same light cone has the same cosmology, but some of these straight lines are pretty long. And in the little inset, we're showing that about 10% of the time, you obtain a shift of 0.2 in omega m. So it means that 10% of the time, which is within 2 sigma, the best fit recovered value is 0.2 away. If you look at 2-point correlation functions or peaks. So this is a statistical fluctuation. So it's fully consistent with the left picture. So it means that we were possibly sometimes some kind of unlucky to have this shift happening. There's also something else which is at play here, is that the intrinsic alignment is not fully modeled for the peak statistics. This is something which is difficult to do, and there's a lot of ongoing work. But I would say stay tuned, because it's pretty promising. This is the result from the data. Constraint on S8 from the 2 peak correlation functions are 5.7% measurement, but if you look at the peaks, it's 4.8. So it's a 15% increase in constraining power with the same data. So it means that no cost in telescope time. You just reanalyze the data a bit differently, and this will increase. This gap will increase with future data, where the filaments and the environment will be more visible in the data. So the factor of 3 that I quoted earlier with Euclid will start to creep up in the next generation of this measurement. So I would probably conclude here, saying that when we do forecasts on dark energy equation of state, the lensing PDF and the peak counts and then shear correlation functions can perform up to 3 times better than the cosmic shear alone, and 2 times for S8 measurements. There's a new way to do tomography that's important to use in future data analysis that improves the forecast by 50%. And then we've applied these techniques to the DESIO 1 data. We look at loads of different systematics, which I've skimmed today. And then basically we can outperform the 2-point correlation function measurement by 15 to 20% we had to exclude a bit of the data. And then we know there is some residual systematic that's present. It's completely subdominant unless, except for the intrinsic element of galaxies, which is not well modeled, which is why we had to exclude some of these cross-tomographic bins. But there's a lot of ongoing effort within KiDS, Euclid, and LSST to address this issue. Thank you.
Okay, thank you very much for your nice talk. I think we have only time for one question. If anybody has question, please raise your hand. Okay. Thank you very much again for a very nice talk. Okay. Our next talk is by Naomi Robertson, and she will talk about KiDSxACT Planck CMB lensing galaxy or galaxy weak lensing cross correlation. She sent us a video. Would you please play it? Thank you.
Today I'd like to talk about the CMB lensing galaxy weak lensing cross correlations project using data from the Atacama Cosmology Telescope and the Kilodegree Survey. The effect of lensing by large-scale structure is to modify the statistical properties of the CMB anisotropies, as well as the apparent shapes of galaxies. So both of these datasets probe an overlapping volume of the underlying matter density field, and so are therefore correlated. But the data and methods for reconstructing the convergence field in each case is very different, and therefore the cross-correlation won't be affected by systematics in either datasets in the same way as the autocorrelations. The galaxy weak lensing kernel peaks at around a redshift of 0.7 for current datasets, and the CMB lensing kernel is broad and peaks at around a redshift of 2. And so by measuring the cross-spectrum between these two, we are directly studying the mass distribution at an intermediate redshift of around 1, just from gravitational lensing. So along with constraining cosmology, this cross-correlation measurement can help calibrate residual biases present in the galaxy weak lensing data. These include potential errors in the shear calibration correction or the multiplicative bias, and the galaxy redshift calibration, which corrects for the imperfect match between photometric and spectroscopic redshifts. As the CMB lensing kernel is well defined by the underlying cosmology, cross-correlation analyses can potentially unearth unknown systematics, providing an independent validation of more standard galaxy weak lensing calibration methods using mock catalogs and image simulations. So for the current measurements, it's common to compress the cross-correlation measurement into an estimation of a single amplitude parameter A, which is shown here. So A is equal to unity if the data are consistent with a ΛCDM model at a chosen cosmology. So for the majority of these previous measurements, the amplitude A was calibrated on the Planck specific cosmology. And as you can see here, for most cases, this appears to be on the low side compared to expectations. Potentially, this could be explained by intrinsic alignments. So the cross-correlation of the intrinsic alignment of galaxies with the CMB lensing convergence produces a negative power spectrum, leading to a reduction in the galaxy lensing CMB lensing cross-correlation amplitude. And studies and simulations have shown that this is expected to be around a 10% effect for current galaxy lensing samples. So in this work, we're looking at the cross-correlation measurement with galaxy lensing data from the kilodegree survey, or KiDS, and CMB lensing data from the Atacama Cosmology Telescope. So KiDS is a recently completed optical wide field imaging survey, which uses the VLT survey telescope shown here. So we heard about KiDS earlier on in the week from Marika Asghari, so I won't go into any details here. So for our fiducial analysis, we include all galaxies with a photometric redshift from 0.1 to 1.2. We also measure the cross-correlation with an additional high redshift sample with galaxies that have a photometric redshift in the range of 1.2 to 2. And these redshift distributions are shown here in this lower plot. So this second sample at a higher redshift has not been used in any KiDS analysis so far. And with this sample, we investigate the accuracy of the shear and redshift calibration. The mean of the redshift is about 0.7 for the main sample, which has an effective source galaxy density of about 7 galaxies per square arc minute. And the higher redshift sample has a mean redshift of about 1.2 and an effective source galaxy density of about 0.9 galaxies per square arc minute. So the CMB lensing map used in this analysis is reconstructed from a subset of arc-minute resolution maps of temperature and polarization data taken by the Atacama Cosmology Telescope. And these maps are now publicly available on Lambda. The area from ACT lensing maps, which overlaps with KiDS, is in the KiDS North area, and this covers a massed area of 275 square degrees. Now, since ACT only overlaps with this KiDS North patch shown in the top panel, we additionally cross-correlate with the KiDS South data with the publicly available CMB lensing maps from the Planck 2018 data release. The Planck convergence map has complete overlap with the KiDS data. However, we only use it on the KiDS South region, providing an additional area of around 450 square degrees. So we use the public code NAMASTER, which is a pseudo power spectra estimator, for this analysis. The covariance of the cross-correlation power spectrum is estimated using a suite of ACT and Planck CMB lensing simulations. These simulations do not correlate with the foreground galaxy weak lensing signal, which is adequate for this analysis since the CMB lensing autospectrum and noise spectrum dominate the error budget. We use the Core Cosmology library to model the cross-correlation power spectrum, but extend this framework to include systematic effects present in the galaxy weak lensing data. Errors in the photometric redshift distribution are typically accounted for by modeling this uncertainty as a shift in the mean of the redshift distribution. Since we're cross-correlating with CMB lensing, we expect it to be more sensitive to the high redshift tail rather than the main body of the distribution. So this shift shouldn't be understood literally as the error on the redshift distribution. Weak lensing shear measurements are calibrated to account for biases introduced by the pixel noise, object selection, and galaxy weights. So the KiDS calibration correction is determined by analyzing mock image simulations of KiDS, and we account for the level of uncertainty in the measured calibration correction by introducing a nuisance parameter m, which multiplies the cross-correlation power spectrum. We also include the effects of intrinsic alignment using the nonlinear alignment model, building on work presented in Fortuna et al. 2020, which predicted the intrinsic alignment signal for a KiDSxACT survey using parameter constraints inferred from recent intrinsic alignment measurements. So across spectrum measurements using galaxies in the photometric redshift range of 0.1 to 1.2 are shown here, where the solid maroon line corresponds to a Planck best fit cosmology, and the orange line corresponds to KiDS best fit cosmology. So these are the predictions from these two data sets. So combining both measurements, we obtain a combined significance of 5.3 sigma, and this exploits the independence of both measurements since they involve different areas of sky. So we first performed the single parameter fit constraining the amplitude A of the cross spectrum relative to a Planck cosmology, which I mentioned at the start of this talk. We consider an intrinsic alignment amplitude of 0.54 as our fiducial value, as motivated by the Fortuna et al. 2020 study. And performing this combined fit, we find A equal to 0.69. This is again low compared to 1, and but is consistent with previous cross correlation analyses. So here we perform a 5-parameter joint fit to the cross correlation spectra. Our constraints on the galaxy weak lensing systematic parameters are dominated by the imposed informative priors, and given the relatively low signal to noise of our measurement, we would not expect to be able to constrain both cosmological and galaxy weak lensing systematic parameters simultaneously. Our constraints are presented here with the right-hand plot compared to the KiDS 1000 cosmic shear constraints shown in blue. Weak gravitational lensing is mainly sensitive to the parameter combination S8, and which we find S8 to be 0.64, which is consistent with the KiDS 1000 cosmic shear analysis. So when considering galaxies with a higher redshift in a photometric surveys, it becomes increasingly difficult to calibrate both their redshift and their shear estimates. Because of this, galaxies with a photometric redshift greater than 1.2 were not included in the nominal KiDS 1000 cosmic shear analyses. Cross correlations with CMB lensing have been identified as a potential calibration tool at these higher redshifts. And so we investigated here by repeating our measurement with galaxies from the KiDS high redshift sample to find us having a photometric redshift between 1.2 and 2. Given the current noise in the CMB data, this calibration method for KiDS 1000 redshift distribution is expected to be noisy, and it's likely that an alternative calibration methods will be more competitive. Nevertheless, this constitutes an essential validation test. So using the same tools as for the main analysis, we measure this high redshift cross correlation signal at a combined significance of 7 sigma. This is shown here in the left plot compared to the predicted model for a Planck and a KiDS cosmology shown as the solid maroon and orange lines respectively. We follow the same modeling methods as before, but here we fix the cosmological parameters and constrain just the shift in the mean of the redshift distribution, or delta Z, and the multiplicative bias M, for which we set wide priors for. So from the figure on the right, we can see that one or both these corrections are preferred to be non-zero. So some offset in the mean redshift distribution is anticipated from the current implementation of the redshift calibration method, since the spectroscopic redshift calibration sample is incomplete at such high redshifts. And many galaxies with photometric redshifts greater than 1.5 do not show strong spectral features in the optical bands and are therefore end up being assigned no spectroscopic redshift. As a result, our selection contains many real KiDS galaxies in a high redshift tail, which are not captured by the current implementation of the redshift calibration method. And so a positive value of delta Z is expected. So highlighted here are a range of values for M based on our current expectations from image simulations, and this is shown as the gray band. From this, we anticipate that the multiplicative bias parameter can be constrained to better than 0.1 for this tomographic bin. The preference for a positive shift in our measurement of delta Z indicates that the mean of the redshift distribution has been underestimated due to this missing contribution from the high redshift tail. So in this analysis, we measure the cross spectrum between ACT and Planck CMB lensing data and the KiDS 1000 weak lensing catalogues. We can expect these cross correlation analyses to become increasingly valuable in the future, even with the current data sets from ACT and SPT, with the final data releases from KiDS, Dark Energy Survey, and Hyper Supreme Cam, which will be tens of sigma. Then looking a little bit further to the future, we'll have almost complete overlaps between surveys such as Rubin Observatory and the Simons Observatory. Thank you for listening.
Okay,
Today I'd like to talk about the CMB lensing galaxy.
Okay. Thank you very much, Naomi. I can see Naomi here. Okay. Hello, nice to meet you. And thanks for your very interesting talk. Okay, we have a question from Alex. Alex, please go ahead.
Thanks, hi Naomi. Thanks for the talk. I just wondered, does your measured cross-correlation amplitude depend on whether the SZ is projected out of the temperature maps before the lensing reconstruction or not?
So we produced our, we did the analysis with the ACT maps where the SZ hadn't been projected out, and found that this didn't change any of our results in this case.
Okay, thanks.
Okay. If no questions. Okay, let's thank Naomi again. Thank you very much.
Thank you.
Our last talk in this session is by Benjamin Giblin. He is talking about KiDSxACT, a robust weak gravitational lensing dataset, and I think he has also a recorded video. Could you please play it? Okay, thank you.
Hi, my name is Benjamin Giblin, and I'm a postdoc at the University of Edinburgh. In this talk, I'm going to be presenting KiDS1000, which is the latest weak gravitational lensing dataset from the Kilo Degree Survey, or KiDS for short. Specifically, I'm going to be talking about the ways that we have validated this dataset and made sure that robust cosmological parameter constraints can be drawn from it. So much of what I'm going to be saying can be found in a paper published last year, Giblin et al., which is on the archive at this address. So in this talk, I'm first going to briefly present the concept of cosmic shear, which is testing the cosmological model with weak lensing. I'll then go on to present the new dataset, KiDS1000, before talking about the ways in which we've validated KiDS1000. And specifically, I'll be focusing on the ways we have made sure that the measurements of the galaxy shapes in this dataset are accurate. So, as I briefly mentioned just then, cosmic shear is the shorthand for probing the standard model of cosmology with weak gravitational lensing. So the way this works is essentially that we have millions of distant galaxies, the light from which passes through the large-scale structure of the universe on its way to be detected by our telescopes here on Earth. Because that light passes through regions of the universe where there is warped space-time, that light, the path of that light becomes deflected, and this manifests in very small distortions in the shapes of those millions of distant galaxies. And these distortions that arise from weak lensing we call shear. So essentially, we measure the shapes in all of these distant galaxies and the correlations in their shapes in order to extract this shear lensing signal. And that lensing signal is sensitive to cosmological parameters. Specifically, it's quite sensitive to the mass energy density of the universe, omega m, shown on the x-axis here, and the amplitude of density fluctuations, sigma 8, shown on the y-axis. And these three banana-shaped contours all come from weak lensing. These are the latest constraints from the Kilo Degree Survey, which were published in Marika Asghari's paper last year. So the key thing to take away here is that there's a discrepancy between the lensing constraints and the constraints which come from the Planck collaboration, who of course observe the cosmic microwave background. So in order to make sure that this discrepancy is genuine and perhaps indicative of an incompleteness in the standard model of cosmology, we need to make sure that our weak lensing data sets are robust and that the cosmological parameter constraints we derive from them are reliable. So KiDS1000 is named this. It's named this because it spans 1000 square degrees on the sky. And the images that go into this data set come from the VLT survey telescope, which is at Paranal in Chile. The galaxies in this data set were imaged in 4 optical bands using that telescope, the VST. But these galaxies are also imaged in 5 near-infrared bands with the Viking survey. So overall, KiDS1000 comprises the shape measurements and redshift estimates for 21 million galaxies. And in this talk, I'm not going to talk about the ways in which the galaxy redshift estimates have been validated. Instead, I'm going to just focus on the galaxy shape measurements. So the first thing we need to sort of make sure that we've got right, if we're going to measure these galaxy shape measurements correctly, is modeling of the point spread function, or PSF. So the point spread function is essentially just a measure of how the light from a point source, i.e. a star, spreads out due to that light having passed through Earth's atmosphere and the optics of your telescope. So this is illustrated by this diagram here. We start off with a point source on the left-hand side, and then the light from that point source spreads out due to it passing through the atmosphere and diffracting through the optics of the telescope. And then that light is incident on our CCD, which of course pixelizes that image and introduces sources of noise. So to measure the galaxy shape measurements correctly, we need to model this point spread function and remove it from our imaging. So the way we model the point spread function is by parameterizing the shapes of the point sources using 2 ellipticity components. These are epsilon1 and epsilon2 shown in these 2 panels here. So these panels are showing the PSF distortion as a function of XY position on our camera. So we can fit a 2D model to these PSF distortions and then remove that from the imaging, which gives us a measure of the PSF residuals. That's what's shown in this lower panel here. So the first promising thing to note is that the PSF residuals are much smaller and they're fairly featureless across the camera. But in order to make sure that this isn't a problem, we need to propagate these small PSF residuals to biases on our cosmological parameters. So if your PSF modeling goes wrong or is done inaccurately, it will bias your weak lensing measurement. And that weak lensing measurement is often a shear correlation function. So this is a measure of how correlated galaxy shapes are as a function of their angular separation. And there's lots of different prescriptions for how imperfect PSF modeling biases that shear correlation function. So some of those biases are shown on this plot here. On the y-axis, we have the bias to the shear correlation function. And on the x-axis, we have the angular separation of galaxies. The 3 different colored lines are 3 different prescriptions for how imperfect PSF modeling biases this correlation function. And these are shown relative to the uncertainty on the shear correlation function, which is the yellow band. So, for example, the magenta line here is quantifying how instrumental defects in your CCD can give rise to a flux dependence in your PSF modeling. And if not taken into account, that flux dependence causes a bias in the shear correlation function. So essentially in this recent paper, Giblin et al., we quantified all of these different biases that arise from PSF modeling, and we essentially measured them for our data set. And then we propagated those biases through our cosmological parameter inference pipeline in order to see how big these biases are in terms of how they manifest in shifts in our cosmological parameter constraints. And the good news is for KiDS 1000, because the PSF modeling is done very accurately, these biases are actually quite small, and they cause essentially negligible changes in the cosmological parameter constraints. When I say negligible, I mean less than a 0.1 sigma change in those cosmological parameters, the mass energy density omega m and the clustering parameter sigma 8. So to conclude, accurate cosmology constraints from weak lensing require you accurately measure galaxy shapes. And KiDS 1000 has been through numerous systematics checks, many of which I haven't discussed here, but can be found in the recent paper Giblin et al. And the good news is that residual systematics in the data seem to have negligible impact on cosmological constraints. KiDS 1000 is also publicly available. It can be found online at this web address, or by contacting me, I can give you access to it. And the last thing I'll draw attention to is that KiDS 1000 was the subject of a number of papers that hit the archive last year, and many different aspects of the data are explored in detail in these papers. And I encourage you to check them out if you are more interested. Okay.
Hi. Okay. Thank you very much, Benjamin, for very interesting talk. And we are very glad to have you here. If anybody has a question, please raise your hand. Okay. Okay. It seems that nobody have question. Okay, let's thank Benjamin again, and this is thank you very much, Benjamin. This is the last talk of our session, and I hope that you find these talks interesting. I think Nima, I should leave the session to you if you have any announcement.
Thank you, Shao. Thank you all the speakers of this session. And no, not really. So we can finish this session, and we can wait for the next session. You know, just let you know that as I told you, the Starkman talk will be the first talk in the second session. Okay, so we replaced this talk a little bit. So in half an hour, I guess. Now it's 6 p.m. Tehran time, and it should be, yes, exactly at 6:30. We start with Starkman. Thank you very much.
Okay, thank you.
Thank you, Shao.
Thank you. Bye.
Bye.
Andreas, I think, yes, you have a question.
clarify if I need to check my video in preparation for a talk.
Okay,
Just that.
that's good.
Hello, András. Yeah, we've received your video, pre-recorded video, and we have it. It's on the system. We will play it when the time comes. And it seems that your microphone is okay, yeah?
Yeah, if you can hear me, I think so, yeah.
Yeah, I can hear you. Do you want to turn on your webcam so we can see you too?
I'm wondering why that is not working.
Oh, sorry, that was me. I think I forgot to give you the permission. Can you do that?
Okay.
Oops, really
Yeah.
sorry.
I
Yeah,
guess.
yeah,
No,
it
no,
works.
no problem. Okay, so it seems to be working. So one question, when the video is played,
Yeah.
could you switch to the PDF? Maybe if, if in case I need to go back the slides or something.
Yeah. I can upload the PDF too, and then you should open it yourself. On the top right, you have an option. It's called Files. You will have your file there, and just go there and click on the play button. It's not there right now, but
okay, but it will be okay.
Yeah, it will be there.
Okay, then I guess
Yeah,
we
it
are
seems
set.
that everything is okay.
Okay, thank you. Talk to you soon.
Thank you. Yes. And Mima.
Hi, Puyan. Can you hear me?
Yeah, yeah.
Yeah. So yeah, I just wanted to suggest that you can play the music because the other session, I mean the room number 2 is not finished yet. So
Yeah.
yeah, thank you.
You're welcome.
Hello, everybody. Hi, Glenn. Hello, Glenn. Hi, Glenn. Can you hear me? Okay. Because Puyan, we do have Glenn's file on our system, no?
Yeah, it's uploaded.
So yeah, so because we have checked it already last night, so maybe we can just play the music and then in 10 minutes we can start.
Hello, Nima. Can you hear me?
Sadar, yes.
Okay, let me check my voice and also my video.
Please, yes.
And show that everything is working.
Yes, sure.
Hello. Can you see me?
Yes.
Okay.
The video is fine. The voice is good. Yeah.
Okay, thank you.
Thank
And where is the Glenn?
Glenn is around because he switched on his video.
Okay.
He should be around. Yeah. So, but we have 10 minutes, 12 minutes. So.
Okay, we have time. Take your time. Okay, don't worry. Okay, I will come back.
The room is not finished yet, so we should wait for them to.
Okay.
Okay, thank you.
I will come back later. Okay, see you.
See you. Hi, Armand. And okay, Puyan, maybe you want to play?
So now we are done with the second room. We are
good. Thank you very much, Shant, and all the speakers there. And because we have 10 minutes, so maybe we can play the music, waiting for the next session. Go, Puyan, please. Yeah. Okay, great. Glenn, can you hear me?
I can.
Yes, perfect. So the chairperson is Sadek, but before that, do you want to play your file? You should go to...
Hello, Keeleey.
Hello.
Nice
All
to
right.
see you. I'm
Great to
Sadek.
see you. Wow. Very
How are
nice
you?
to see you.
Thank you. Thank you very much. I'm a chairman of this session.
And now I have to find, of course, my
Yes.
file.
Could you find it?
Yeah, I just found it.
Okay.
There it is.
That's perfect. Okay.
Good. So
we will.
It's for you, Sadek. Thank you.
Thank you, Nima. Thank you. Thank you. Hello, Glenn. And nice to meet you and see you here.
Nice to meet you. I'm
Thank
sorry
you.
it's not in person.
Yeah. So due to this pandemic, unfortunately, pandemic has many disadvantages, but some of the advantages of this pandemic maybe provided such opportunity for us to provide in such a virtual meeting here. Okay.
Absolutely.
Yeah, okay. So we will start at 6:30.
Right.
Okay.
And it looks like the meeting's been going wonderfully. I'm sorry I haven't been able to come into more of it. That's the one bad thing about Zoom conferences is administrative duties can distract you away because you're not there.
Yeah. Thanks to Nima and another organizer, they work very hard to provide such opportunity for student, for teacher in Iran and through the world. Okay.
Exactly.
So I think that it is better to start. Okay. So hello everybody, and hope all of you to be fine and healthy during such pandemic. And also I hope that you have found this virtual meeting to be useful until now. So I'm Sadek, I'm the chairman of this session. Welcome to the second part of the fourth day of this conference. It's my pleasure to introduce Professor Glenn Starkman. He's going to talk about an uncooperative universe, largest scale anomaly in the CMB. Okay, you can start. Thank you.
Great, thank you. It's wonderful to be here. I'm sorry I can't see all of you, but I'll just imagine you out there. So I'm going to talk about work that I've done with a lot of people over many years, about our wonderful universe and our fantastic theory, which tells us so much and agrees with so much that we see, but doesn't agree with everything that we see. And I'm going to talk, and I'm going to tell you about something that we don't always talk about. Recently we've been talking about things like the H0 anomaly and related ways in which we're perplexed about the universe. But I want to tell you about something completely different that could ultimately shake the foundations or lead to major discoveries about the early universe or about the universe today. So, of course, we've been looking at the cosmic microwave background for over 50 years. From its discovery to the fantastic maps that have been made in this century. We started with this map almost 20 years ago, and now we have the Planck map of the entire sky, and it's an incredible achievement of our technology and our ability to look out and dedication looking out at the universe. And one of the things we're taught in kindergarten, or at least cosmology kindergarten, is that when you have a map like that, what you're supposed to do is you're supposed to decompose, which is, of course, a map of the temperature fluctuations on the sky. First what I've done is I've taken the full sky and cut it open and stretched it out and put it flat on this screen. What you do when you have a map like that of the temperature on the sky is you expand it in spherical harmonics. And you've probably seen that many times if you're a student of cosmology. Why do we do that? Well, we do it because our theory tells us to. It tells us that our standard model for those fluctuations, which the origin of them, which is called inflation, tells us that the sky is statistically isotropic. Okay? It's not isotropic, obviously, you're measuring anisotropies there, but it's statistically isotropic. And what the theory tells us is about the statistics of these ALMs, these coefficients of the spherical harmonic functions. Okay? It tells us that they're independent Gaussian random variables of zero mean. That means that the expectation value of the product of any two of them is zero unless they're the same one. And then it's only dependent on this index L and not on this index M. And so all of the interesting information in principle, according to our theory, on the sky is contained in those CLs. Now, of course, that's not quite true. There could be non-Gaussianities. There are other things in the foreground. But to leading order in our theory, the interesting information, the thing we want to measure are these CLs. And it's amazing what we've done. You know, here is at this point a rather old, but about 8-year-old plot of the temperature angular power spectrum. And you'll see all these amazing bumps and wiggles, really well produced by the underlying curves. You can barely see the curves because they're sitting there under the data, that only take us 6 or maybe 7, I would argue, parameters to fit to far more than 6 independent points. And of course, I haven't shown you the temperature E-mode cross-correlation or the E-mode E-mode cross-correlation. And the same thing is true of all of those. So 6 parameter fit to far more than 6 points. So this is an astonishing experimental accomplishment. And what we find is in remarkable agreement with the theory, especially, I would say, for statistics that the theory tells us to look at. But there's a but. So I'm going to tell you about some of those buts, focusing on ones that I've been particularly interested in: alignments at low L and the failure of statistical isotropy. What is often called the low L, but I would call the large angle problem, which is the vanishing of the 2-point correlation function. And I'll briefly mention, because we only have 30 minutes, a couple of other things that I think are also strange. So what I'd like to suggest is that there are troubles in this cosmological paradise that we live in, or at least that there may be, and how we might be able to tell, and how we are getting hints that they're really there. So I think the first hint came a long time ago, and if we look back, it was even older than that. The first hint was often called the low L anomaly, and if we look at the 2-point angular power spectrum of temperature as measured by the WMAP team, this is their year 1 release. What you'll see here is points. Those are the C sub L's, or rather, you'll notice that since there's supposed to be 100, we're going up to L of about 1,000 here. There aren't 1,000 points, but these are binned C sub L's, binned over sufficiently wide ranges that each of them is approximately independent. And you'll notice that there's lots of data points. There's a theory best fit that goes through them. There's a gray band, which is our cosmic variance, our error bars, due to the fact that we only have one universe that we can look at. And so it's pretty narrow up here at large L, where there's 2L, where at 400, there's 801 different ALMs of a fixed L, and much wider down here, where at L equals 2, there's only 5. But one thing you'll notice, and was certainly noticed back then in the early 2000s, is that C2, the quadrupole, is very low. Okay? And C3 is kind of low, okay, within the cosmic variance error bands, but still low. Now, that's not a lot to hang your hat on, as the expression goes. There's not a lot to start thinking about and working on it, but it got people intrigued. Maybe it shouldn't have from a statistical point of view, but I'll argue that it's actually the hint of something much more significant. And so we started looking at beyond the C sub L's to search for departures from this prediction of our model that we live in a statistically isotropic universe and that the ALMs are Gaussian. And there are many, many ways in which people have done that. I'm going to focus on one here because I had some role in that, but there are many interesting ways in which people have done that. And so I'm going to talk to you about alignments of multipoles. Okay? And the question we set out to ask way back then was, what directions are associated with the Lth multipole? We had reasons for asking that question. It wasn't just a fishing trip. We were actually trying to search for the topology of the universe. But anyway, if you look, for example, at L equals 1 at the dipole, we don't usually talk about A1M. What we usually talk about is the direction of the dipole, which I've represented here by this unit vector, U hat 1, 1, and the amplitude of the dipole, rather than these A1Ms. And the advantages is that U11, U hat 11 is a unit vector and A is a scalar. And there's a relationship between A and the usual dipole's power. So what about other multiples? Well, in general, you can write the Lth multiple as a product of L dipoles and then subtract all the appropriate traces. So you can replace the 2L plus 1 ALMs by L unit vectors and 1 overall amplitude. And those unit vectors, well, they're not quite randomly distributed on the sky, but certainly the unit vectors, these multiple vectors of one L are supposed to be completely independent of the multiple vectors of the other, and they are supposed to obey their own specific statistics within each L. So rather than talking about ALMs, we could talk about these multiple vectors. We thought we were very clever in inventing this completely new way to think about data on the sky. It turns out that you may have heard of this fellow Maxwell. He wrote this little regarded textbook here, or text here, a treatise on electricity and magnetism, in which this is precisely how he thought about data on the sphere. So not so old, not so new an idea, but an oldie and goodie, Maxwell multipole vectors. Okay. Now, so the quadrupole can be thought of as represented by two vectors. In other words, you can think of it as a plane. And so we could talk about the normal to that plane, or the cross product of those two vectors. So we can think of that as the area vector of the quadrupole. The octupole has three vectors. You can think of the octupole as having three planes, and so three normals to those planes, three area vectors that contain some, not all of the information of the multipole vectors, but most of it. Okay, and so I want to plot for you those area vectors. Okay? I want to show you where they lie on the sky. And I'm going to do that in an old projection that no one uses anymore, because we promised one another that we wouldn't replot this in ways that people thought we were going to be adjusting it to make it look more compelling. So this is how we plotted it way back in about 2005 or 6. So here is the galactic north and the galactic south and the galactic equator. Okay? And you can see a bunch of labeled dashed lines, like the curves, like the ecliptic plane, the plane of the solar system. But what I'm plotting here is, first of all, this is the dipole. This kind of dark gray is the direction that we are moving through the universe, or at least what we interpret as the direction we are moving through the universe. And then, sorry, that is where's the dipole? Yeah, that's that light gray. This dark gray is the direction, is the normal vector of the quadrupole. Okay? So it's sitting right here, kind of near the dipole and kind of right next to the ecliptic. Okay? So that means that the plane of the quadrupole is perpendicular to the plane of the solar system. Now, what's really intriguing is that the three octupole area vectors are, first of all, very close to one another. So remember, the three octupole planes, they could have pointed in any relative directions, but they don't. They're almost parallel to one another. And their average is almost exactly the direction of the quadrupole plane. So these four planes of the quadrupole and octupole, instead of being randomly distributed on the sky, are all pretty much parallel to one another. They also happen to be perpendicular to the solar system and pointed pretty much in the direction that we are moving through the universe. So again, they're aligned with one another, these four planes. They're perpendicular to the ecliptic, and they're normal to the dipole. Now, the area vectors tell about the orientations of the multiple planes. They don't include all the information, as I said. We can rotate these four-line planes about their common axis. So let me show you a picture of what just the quadrupole and octupole look like on the sky. And you'll notice this black curve, that's the ecliptic plane. And I should draw a great circle through all these 6 extrema that are the quadrupole plus the octupole. And amazingly, a great circle would go almost through all of them and be perpendicular to the ecliptic plane. And you'll notice that what's not captured by the area vectors is that the ecliptic plane pretty much traces out this nodal line between the zero between these two extrema. You'll also notice that the extrema in the south are stronger than the extrema in the north, and we can come back to that and remember that for later. So this is kind of unexpected, right? And what's interesting is if you go and now remember that you're supposed to correct not just the dipole. We know that the dipole of the CMB is mostly due to our motion through the universe, or at least we believe it is. But we should also correct the higher multipoles. They get very small corrections, but it turns out the quadrupole gets an important one, and it moves the area vector of the quadrupole here, this red diamond down here, up to this red square up here, just a little bit, but it moves it much closer to the octopole, the average of the octopole area vectors. So it makes the alignment even better, which is something one discovers just kind of after the fact. Okay. And of course, this doesn't change at all in Planck after WMAP, right? This could have all been, especially with the solar system being involved, this could have had to do with the orbit of WMAP or something about the scan strategy. No, this is on the sky. So how unlikely is all of this? Well, of course, it's going to depend on the precise map that you use, but it doesn't seem to depend all that much. So if you ask how likely is it that the four planes of the quadrupole and octopole are as aligned with each other as they are in a random realization of lambda CDM, the p-value is somewhere between about 0.10⁻³ and few 10⁻³. And you say, okay, well, suppose you look at all skies in which the quadrupole and the octopole planes are that aligned. How likely is it that they're this perpendicular to the ecliptic? The answer is, between, somewhere around 1%, between about 0.2 and 2%. And you say, okay, well, suppose I look at all skies in which the quadrupole and octopole planes are that aligned and that perpendicular to the ecliptic. How likely is it that they're pointing at the dipole? A few percent. I say, okay, well, suppose that you look at only skies in which the quadrupole and octopole planes are parallel to one another and perpendicular to the ecliptic and pointing towards the dipole. How likely is it that they would be turned in such a way that the ecliptic passes through, along this zero between two of the extrema, or actually two pairs of the extrema? And the answer is, again, just a few percent. So each of these are independently unlikely things. Which of course means it's very hard to decide which of these is just, maybe all of them are just accidents, but which of them is the one that we're supposed to pay attention to, because one of them, the first one, has to do with cosmology, and the others have to do with the second one has to do with the solar system, and the third one has to do with some combination of how the solar system is moving through the galaxy, and the galaxy is moving through the universe, and so all of this seems to be somewhat of a mess. So it's hard to come up with an explanation. It's hard to explain how this happens cosmologically. How do you get the dipole correlation? It's hard to see how you get this in systematics in both WMAP and Planck. It's very hard to see how the galaxy would produce something that's so correlated with the solar system, and it has the wrong multipole structure to look like something from the galaxy. It's hard to get it from other foregrounds because typically those amount to changing little patches on the sky, and it just doesn't work out right. But these alignments are persistent. They're at least individually interesting and collectively very significant, but it's hard to explain or establish priority. So let's move on. So in fact, I want to tell you about one that I somehow have the feeling is more fundamental. If I was going to ask which of those previous ones was fundamental, it's probably the quadrupole-octopole alignment, and the others are just accidents, but how do I know? So I want to tell you, go back to that original idea, the original observation that we had, you'll remember, which was that the quadrupole was too small, and argue to you that that's not actually what's strange. What's strange has to do up here in angular space, where we're looking at angles bigger than about 60 degrees over these lowest few L's. And what's interesting, before WMAP, actually when WMAP before WMAP there was COBE, and COBE did a much more lower angular resolution measurement of the same sky. And at the beginning of the life of COBE, before people had actually started to analyze the data, people used to think, because they were astronomers, not about the angular power spectrum, but about the angular correlation function, which is the product of, if you have the two temperatures in two directions on the sky, and it's hard for you to see, so I'll back up, on two directions in the sky, you multiply them and then average over all pairs of points on the sky that are separated by the same angle. That's the angular correlation function of the temperature. You can do this with the polarization, or you can do it cross correlations. Now, mostly people have come to ignore the angular correlation function because in principle it contains the same information as the angular power spectrum, just differently organized. Although that's kind of like saying that you should never Fourier transform your data because it contains the same information. The Fourier transform contains, after all, you can just Fourier transform back. You wouldn't learn anything. So here is what COBE saw way back in 1996. And notice, but people kind of, it was the last COBE paper that they put out. They hadn't talked about this in the earlier papers, but they pointed out to us that in all of their bands, that when you looked at the angular correlation function, this is what it looked like. And in particular, notice that it's kind of very close to 0 from about 60 or so degrees up almost to 180 degrees. Now, WMAP went back and looked at the sky, of course, again, and they saw the same thing. But here I'm showing it to you with not just the data, but also the theory. So here's the expectation value. This dotted line is the expected value of the angular correlation function. Now you'll notice this big wide blue band around it. Those are the 1 sigma error bars. And in our theory, of course, the angular correlation function at 2 different angles are not independent, and so I can't put, it's kind of hard to interpret this blue band, unlike if I had an angular power spectrum. But what you'll notice is that there's 2 sets of lines of curves here. There's all these curves that kind of hug the x-axis, the 0 line here, where there's 0 angular correlation between about 60 degrees and almost 180 degrees. And those are the data. Okay? Those are the data, or the reconstructed full sky. The reconstructed sky outside of the galactic plane. If you reconstruct the full sky, you'll find that you don't get quite the same thing, which is kind of odd. Your data here, Q, V, and W, tells you that if you look at the sky that you trust, the part of the sky outside the galactic plane, you get 0 angular correlation function. But if you then go try and reconstruct the full sky, you'll find correlations. But if you just look at the part of the sky that's outside of the galaxy, the part that you trust, you seem to get 0 angular correlation from about 60 degrees, almost all the way up to 180 degrees. So it's not that these are outside of this blue band. They're not that far outside of the blue band. The blue band's really wide, but they're very close to 0. And so they invented a new statistic, which was just the integral from 60 to 180 degrees of c of theta squared d cos theta. They called it S1/2. And that S1/2 is and has remained ever since extremely low, much lower than we have any right for it to be. And it's, it depends exactly which map you look at, but as long as you look at maps of the sky outside the galaxy, okay, that number seems to be somewhere around 0.02 or 0.03%. So a few in 10 to the 4. It's only if you take the full sky, then you find that number is still low, but at a few percent. Okay. And that has not changed. Here it is. The same thing is true in the Planck data. Okay? So this is there on the sky. It's not a systematic question. Okay? It is very hard to get this. If you look at ΛCDM realizations, then you'll find that between 0.03 and 0.1% of realizations of the concordance model of inflationary ΛCDM have so little cut sky large angle correlation. It's really very hard. So either this reflects a 0.1% probable full sky lack of angular correlation, or you just happen to align your sky right so that whatever correlation there was hiding behind your galaxy cut. Now, the real kicker is, if this is true, if this is not a statistical fluke, it's really strange. And that's because the C sub L's in our theory are the sums of squares of Gaussian random statistically independent variables. And so if we replaced all the theoretical C sub L's by their measured values, you'd say, okay, that's really good. If I do that, let me have a theory that just changes the C sub L's by changing the inflaton potential or something like that. Then my new realizations, my realizations of that universe, of that theory, would predict this lack of angular correlation. And it's not true. And it's not true because at low L especially, you have a theoretical CL, but your measured CL is going to deviate from it a lot because of cosmic variance. And it turns out that to get a low angular correlation function at large angular scales requires that the C2, C3, C4, and even kind of C5 have the right relationship to one another, the relationship we see in the data. So this, what looks like just a low C2 and kind of nothing special here, actually this relationship between C2, C3, and C4 and the later CLs is what's responsible for the lack of angular correlation function. And so we actually need the C sub L's of different L to be correlated with one another. And that's really hard to get out of our theory. You can't get it just from changing the inflaton potential or in any other way, just changing what you expect for CLs. You have to break that statement that the ALMs of different L and M are uncorrelated. So what's the explanation? Well, the first explanation is that this is just a statistical fluke. Of course, that would be disappointing. It would be good for the theory, but disappointing for theorists. So the second possibility is that it's physics. But for it to be physics would seem, at least if we want to preserve this notion that the way fluctuations were generated through something like inflation, in which the amplitudes of eigenmodes of the wave operator in the early universe were Gaussian random variables, then the eigenmodes are the wrong ones, right? Or at least that's the implication I draw from it. So the radial function times YLMs are the wrong basis to preserve Gaussianity. So for example, it could be a sign of cosmic topology that the boundary conditions we think we have on the universe, the covering space, infinite Euclidean space, or spherical space, or hyperbolic space are wrong. Okay? That there are interesting boundary conditions that are yet to be discovered. Another possibility is that and it seems very reasonable that large angle correlations vanishing is because large distance correlations vanish. And so perhaps the fluctuations aren't actually Fourier modes, but modes that only have compact support. We thought that was a very interesting idea. So we went and looked at it and showed why it doesn't work. It's kind of subtle. It works until you realize what it doesn't fix. So I'll skip that over unless there are questions. Finally, I want to just mention something called what's often called power asymmetry or dipole modulation, but which I'll call low northern variance. And you kind of can just see it by looking at this map. If you look at this map, you'll notice that there's a lot more going on down here than there is going up here in the north. Okay? And we certainly weren't the first to notice this. Many people have noticed this and thought of this as a dipole. Strong down here, weak down here. But in fact, what's going on is that the ecliptic south is completely normal, right? Here is the probability distribution function in lambda CDM, best fit lambda CDM of the variance in a hemisphere. And here the ecliptic south sits right at the peak of the PDF. And here the ecliptic north sits way at the tail of the PDF. So there seems to be extremely low variance in the north. All right. So there's a couple of other things I don't have time to tell you about, but with so many anomalies, what do we do? Well, The best thing would be to find a fundamental physics model, make testable predictions, and test them. We'll see about that. The second thing would be to at least make reasonable phenomenological extrapolations and test them. The other thing we can do is to test what's called the fluke hypothesis, the proposition that these are all just statistical flukes. In other words, to test lambda CDM. That's our null hypothesis. Let's at least test that. So here is a list of new fundamental physics models that explain all, most, or several of the anomalies. I'll argue that maybe there's one on that list, and that's cosmic topology. So phenomenological extrapolations, that means assume each anomaly is physics and guess what it implies for other observables. And finally, testing the fluke hypothesis. Assume lambda CDM is correct and see how the measured anomalies affect predictions for other observables. So, and those usually go hand in hand, those last two, testing the fluke hypothesis and phenomenological extrapolations. Okay. So, for example, we saw the low northern variance. Okay, that the variance is extremely low in the north and pretty ordinary in the south, completely ordinary in the south. And so we might ask, well, what will that mean for polarization? And a phenomenological guess would be that good chance that if you have low variance in temperature over a large region of the sky, that you get low variance in polarization in that same region. It may not be true, but it's a reasonable guess. Okay, what does lambda CDM say? After all, temperature and E-mode polarization are correlated. It says there's almost no change in the polarization variance distributions. Here is what you would predict, knowing that you have a temperature anomaly, a low variance in the north. Here's what you in temperature. Here's what you predict for E-mode polarization, and you see you get a slight shift, but it's in both the north and the south, and it's really quite mild. So that means that if you go out and measure the variance in E-mode polarization.
Sorry to interrupt you. Sorry, just 5 minutes left. Thank you.
Yes, great. Thank you. Go out and measure that E-mode polarization. That what you would that if you see the same 10%, because notice that this is, if I go back here, the peak here is at about 11,000, but the north is at about 10,000 in some units. Let's not worry about the units. If you saw the same 10% reduction from the full sky, well, here is what you expect. Here's 12.6, and take away from 12.6, 1.2, and you'd be somewhere way off here, off the left of the map, and so that would have an extremely tiny p-value, much less than 0.01%. Okay. You don't even have to have the whole sky. You could, for example, just have the sky from Chile. Okay, and here it is at 12.6 as the expected value, and subtract 10%, and you're way off the bottom. Okay. So this is something that we could test if we can measure the variance reliably over a hemisphere. So you need to create constrained realizations of best fit lambda CDM constrained to agree with the observed temperature anomalies, and then see what that implies for your maps. Okay. So what about the angular correlation function? Well, here, remember, is this angular correlation function in temperature, very, very small, unexpectedly small, between 60 degrees and almost 180 degrees. And so you would expect, perhaps, in a phenomenological model, that the absence of angular correlation in temperature implies an absence of angular correlation in polarization, at least E-mode polarization. And so what does lambda CDM say? Well, if TT is 0 above 60, other correlation functions are going to be affected. That was pointed out, by Dworkin, Paris, and Hu in 2008. Let me jump to this one. What we expect is not much change in the E-mode correlation, because the E is not very correlated with the T. It just isn't. A little bit, but not very much. Okay? So what we expect to find is this distribution, and this would be the ensemble average prediction. And now, amazingly, people have gone out, and this is from a paper that we wrote in about 5 years ago. pointing this out. Actually, here is a plot of what you would get in the QQ and the UU, and put them together into the EE. And here's what you expect, the distribution. Here it is on slightly different axis, on a logarithmic axis. And guess what? Here is the E mode 2-point angular correlation function way off in the tail, not angular correlation function, angular correlation function, the S1/2, far too low. And this is a completely a priori prediction that we made, that if you saw this, it was a sign that there was a confirmation of the TT anomaly, and that anomaly is seen again in E mode polarization. And I should point out that there also are hints of that already in E mode in the northern variants. So let me wrap up. There's some other things we could talk about, but to wrap up, the sky appears not to be a typical random realization of a Gaussian random statistically isotropic field. And this is kind of remarkable given how well the ALMs agree with our theory, how well the CLs agree with our theory at high L. You know, the temperature multiples are aligned with one another and or with the ecliptic or dipole. The temperature sky lacks large angle correlations. There are noticeable hemispherical asymmetries and difference. And there are several other things that are very strange about mostly low L, but even some of the higher Ls. There is no good model so far, certainly not systematics or foregrounds. Cosmology is not really either. I will point out this paper that looked at the study of topology of the universe using multiple vectors and found that the quadrupole and octupole alignments could be due to us living in a finite universe in one direction. And this preprint that pointed out that the same size universe could also lead to an absence of angular correlations. So while the cosmic orchestra may be playing the lambda CDM symphony, someone gave the bass and tuba the wrong score, and they're trying very hard to hush it up. And there's no good theory for any of this yet, but we shouldn't stop looking. Thank you.
Thank you very much for your interesting talk. And we have time for some question and comment by audience and participants. Okay. So, Yashar, let's give the permission. Okay, Yashar, go ahead.
Hi, Glenn. Do you hear me?
I do.
Yeah, okay. Thanks a lot for the great talk. So I have a question general question about all this. One of the criticisms of this anomalies is that, is the so-called look elsewhere effect, right? So basically, my question here is, like, when you're talking about like quadrupole, octupole alignment, and when you're computing the p-value for that, are you assuming, when you're looking at like simulations from lambda CDM, are you only comparing to cases where quadrupole and octupole are aligned, or any multiple, any randomly basically chosen two multiples that are aligned? Because that would reduce the significance, I assume, I imagine, a lot, if you not only talk about quadrupole, octupole alignment. So this is kind of like maybe another question which is related is, like, when you are talking about like combined significance, when you are looking at different anomalies and say, okay, so each one is not maybe very significant, but if you put together, then it becomes very significant. Again, the question is, how are you choosing these anomalies? Of course, if you pick different random things that are weird in the data and then combine them, that they reduce the value a lot. But I mean, that can happen anywhere, right? So
Yeah. So the example I like to say is there's a difference between walking down the streets and noticing the alignment, the license plate that says 001 Prez, and you assume that's the president, and the one that says 1KTJ157, but they're both unique, right? So you're right. We have to be very careful about what look elsewhere effects, which is basically we look up in the sky and we see sheep flying by in the clouds. We look into our tea and we see our future. We have we're very good at seeing patterns like that. So maybe that's just that. So there's a few things to say. First of all, we could have that discussion for a long time. And what I was trying to tell you about these predictions, these testing the fluke hypothesis, is a way of putting that that discussion behind us. Because and what it says is, okay, we saw these anomalies in the temperature map, and we can discuss look elsewhere questions, and I'll answer that part of your question in a minute. But let's go and look what does lambda CDM say once you have that, and what would a reasonable physics model that you imagine say? So, for example, lambda CDM says that if you have a low variance of temperature in the northern ecliptic hemisphere, which has a p-value of whatever it has, but did I optimize over hemispheres, all that stuff, right? But once I know that, what does lambda CDM say for E-mode polarization variance? And it says it'll be pretty much unaffected, right? It's the effects are very small. The change in the distribution. Okay, and now you go measure it, and so if you find a pretty much normal E-mode variance, you learn that the T-mode. You don't learn that the T-mode was a statistical fluke, but you certainly don't have any evidence that it wasn't. But if you go and measure E-mode variance that's again low in the north and normal in the south, that is a prediction of your phenomenological model and an independent anomaly in the lambda CDM, right? Which I at least would be comfortable of multiplying, quote, computing the joint p-value, which would essentially be the product of the p-values. Okay. Now.
Okay, thank you.
So, but the other part of the question is, you asked me what in terms of the p-values I computed, and what's interesting is, and we've done studies of this, almost all the anomalies I've told you about are almost all perfectly statistically independent of one another. Okay, right. In lambda CDM, right? So, for example, the angular correlation function, the S1/2 vanishing, the smallness of S1/2, that has to do with the CLs, right?
Yeah.
Whereas for the quadrupole octopole alignment, doesn't care what the CLs are. It only cares about the relative values of the ALM, about the multipole vectors. Okay, so those p-values have nothing to do with one another. Similarly, when I quoted p-values for the for the quadrupole and octopole, I told you, I said, okay, the p-value of the quadrupole and octopole being so planar and aligned is 0.2%. And if that is, once you have that, if I look in lambda CDM, what's the probability of them being so perpendicular to the ecliptic? Well, that's again about 1% or less, right? So that was a conditional p-value, right? Okay. I could have taken it the opposite way, and the product would have been the same, but each of them would have been different, right? And so I've tried to be careful in quoting numbers to quote conditional p-values where they're dependent, and to otherwise point out that they're actually completely statistically independent in lambda CDM.
Okay, thank you very much. That's great. Yeah, thanks.
Thank you. Sohrab has a question. Okay, go ahead, Sohrab.
Hello, Glenn. Thanks so much for interesting talk. I had a question about this accidentally, the parallel orientation of the multiples, and then with respect to the equatorial plane. And I'm not expert in the analyzing the CMB data, but my question is that, would it possible that this low L aligned multiples coming from very close by structures like dust in our solar system?
So that's a great idea, and of course people have looked and not found anything. However, I should point out to you the difficulty of making that work, right? Which is that ideas like that tell you how to add power, right? They say, okay, suppose the solar system has a cloud of of cold dust around it, but it generates what looks like a CMB quadrupole and octopole, and because it's organized by the solar system, they're aligned, right? And aligned with the solar system. Okay, well, but for that to be the dominant quadrupole and octopole means that there has to be much lower cosmological quadrupole and octopole, right? And remember, those were already, the quadrupole was already too low, and the octopole was at the bottom being low. So you go from saying that there's that the correlations that you see are cosmological to saying, well, actually, all of it is just local, right? So you don't improve the problem, right? And that is one of the difficulties. That is one of the outstanding difficulties of any of the solutions of these problems. That it's very hard to solve them in the foreground because you have the CMB fluctuations are mostly made very far away.
Okay.
But
Thank
good
you.
question. Yeah.
Okay. Thank you. Powell has a question. Okay. Powell, go ahead. Just ask you to maybe summarize your answer to a question. Okay. Thank you. Go ahead, Powell.
Yes, thank you. This was most stunning, I think the alignment with the ecliptic is completely crazy. Obviously, yeah, it just cannot be.
I would guess that's a fluke.
Yeah, but it's just too good a fluke, right? But here's my well, it's a question comment, and I'm not sure if this helps at all, but. In terms of interpreting the CMB, Wawrzyk wrote an interesting paper in 2018 in Monthly Notices. It's called Universe Opacity and the CMB, and he calculates in that paper by taking into account the fact that there is some dust between galaxies, the cosmological combined flux from all this dust at cosmological distances, and he shows in the calculation that one gets a flux of infrared photons and photons in the radio, which is the CMB. So either he's made a major error, he takes the observationally inferred density of dust, intergalactic dust, which one gets from quasar absorption lines and so on. So he doesn't adjust parameters to do so, so this would then imply that if one subtracts the dust photons from the observed flux on the sky, there's nothing left, right? Now, therefore, we would have no observational evidence for hot Big Bangs. So either Wawrzyk has made a very big mistake in the calculation, or we have a very big problem. Now, I don't understand. I would not know how.
I presume this is a question to me, so let me respond.
Yeah.
So extraordinary claims like that, or like mine, require extraordinary proof. I would say, that an idea like that requires you to explain all of the things that that lambda CDM explains, right? So, for example, it's extremely, and it's similar to trying to explain dark and replace dark matter by Mond on if you want dark matter to also work on cosmological scales. Like, you have to explain everything, right? So you have to explain, for example, why the hundreds of independent CLs of temperature, and temperature E mode and E mode are fit by the 6 parameters of lambda CDM. So that would be.
I completely agree with you, totally. I mean, I'm not saying,
right.
But the point is the dust is there and it's radiating.
Right. Well, the point, right.
Yeah,
but so that what that suggests, of course, is that he's made, that he's overestimated the emission from the dust.
Well, so far I have not been able to find a mistake, and I'm very worried about this. Yeah, and now assuming it is dust, I agree that what you said, one has to explain all those correlations and the power spectrum. Now he goes into that and he shows that it's actually possible because the fluctuations you would deduce in the dust emission are actually very comparable. But I'm not sure how this would affect your problem, the problem which you've been talking about. Right? That's the sort of issue. Maybe that would help, maybe not. I have no idea. But I just wanted to point out that this work exists, and it would be wonderful if an expert like you might look at it, and maybe you can find an error and let us know.
Right.
Yeah.
Yep.
Thanks.
Sorry, since in order to better manage the time, I asked to all of the questioner maybe ask a short question. Okay. So go to the next person, Richard. Okay, go ahead. Just please ask short question. Thank you.
Dick, you had a question?
We cannot hear your voice, Richard.
Dick?
Okay, go.
I think
Go
that's
to
me.
the.
Hi, Glenn.
Yeah, I think
Dick
it's you,
Bond.
Dick. Yeah. Jay Richard.
I'm like you. I am not. I think it's an important issue to raise the anomalies because they are there on the sky. It's real. Shiji Wang, who's on this meeting as well, and I looked at this a number of years ago, and we've talked a lot about it. But recently, I've gotten interested from the point of view of large-scale structure in, and this is not surprising, inhomogeneities in trajectories of C of theta. In that case, it's trying to be 3D correlation functions, but often in projection. So the S1/2 statistic is an integral of C squared of theta d cos theta.
Mm-hmm.
But you can also construct, as well known, BIPOSH does some of this at some level. You have a pole that you do your measurement and run of C of theta from, and then you let that pole run around the sky. And I think that there's really interesting information in the fluctuations of those trajectories, as well as the mean value of the trajectories. And I don't think this has been looked at, but the S1/2 statistic is sort of trying to go in that direction at some level. But I'm just wondering at what level people have looked at it. If I do a naive interpretation, it seems like the low C of theta over that broad theta regime also, I would guess, seems to have relatively cold fluctuations around it for reasons which I don't understand, but I think you'd have to really go into the statistics in much more detail to make that a more definitive comment. Have you thought about, you know, that sort of higher order statistics? Because that involves, of course, quadratics.
Yeah,
as opposed to,
I
sorry,
haven't done a lot. I
quartics
started
as
down-
opposed to quadratics. And
Yeah,
at
thanks
some
for-
level, C of theta given position on the sky, if you mark those positions, that would be like 3 point.
Right. Yeah. Thanks, Dick. Great question. So Tiago Pereira and I and
You're sort of breaking up.
Can you hear me? Can people hear me?
Yes, yes, I can hear
Okay.
your voice. Okay,
Great.
go ahead.
So Tiago Pereira and Armando Bernoulli and I, we started heading down that direction, and then and you know, wrote down some stuff about statistics. But basically, it was like what you said with, you know, with circles around points. I think it's really interesting. We kind of got distracted because we were so excited about this result. As you know, since we were there at the same time at the same talk that got us all reinterested. I probably think you reinterested in topology of the universe way back at CETA in the 1990s. But we got distracted, and I think for good reason, in this idea that that topology actually has the potential for explaining a fair number of these things, and then maybe therefore telling us which ones are real and which ones are likely to be flukes. But yeah, I think you're absolutely right. I mean, and that's, after all, in a topologically non-trivial universe, you spontaneously break the statistical isotropy and the homogeneity generically, and so now it's not just things like C of theta that's interesting, but a map, if you like, of C of theta, you know, with different centers. And so absolutely, I think it's actually, especially now with the polarization data getting so much better on large angles, that it's time to go back to a lot of, you know, some of the things we were thinking about a decade ago, and really make a push towards using the data the universe has given us to try to understand this question, because there's so much there on the sky that's hard to understand, and I don't think I don't think it's all just tea leaving. And I think we're starting to see that with things like evidence that the vanishing of EE correlations and low northern E mode variants.
Okay, thank you. Since we are running out of time, the next question will be the last question. Leon, go ahead. Okay, thank you. Please ask your question.
Glenn,
okay.
So, can you hear me? Yeah.
Yeah,
yes.
Great to hear you.
So Craig Hogan gave a talk.
Yeah,
and I just to quickly get my question out there. Do you have anything to say about Craig Hogan's efforts to come up with an explanation for low SIF?
Yeah, every time I try to understand them, I don't quite. So I'm clearly not as smart as Craig.
It's okay. Same experience as I've had. Thanks.
Okay, thank you very much. Thank you again. Let's thank again the speaker virtually by clapping. Thank you very much to all of you.
Thanks, everybody.
So we have to finish this session, and hereafter the second part of the contributed talk session will be started in the 2 parallel room. I asked the organizer to ping the address in the chat box to select which room do you want, that you want to go through that. Is there any comment by organizer Nima?
Not really. Now Puyan will send the address for the room 2, but let's wait for 2-3 minutes that then people can decide on in which room. Yeah, please. Thank you, Sada.
Thank you. So we will start 2 minutes later. Okay, thank you. So I think that in this room, the András Kovács, if I'm right. Okay, raise your hand. Okay, I know that. Puyan, please give the permission to the András to check everything before starting the next session. Puyan, can you hear me? Okay, hello. Can you hear me?
Okay.
Can you hear me? Okay.
Yeah. What about? Can you hear me?
Yes, of course.
Good.
You have uploaded your file in our system, or you are going to share your desktop?
I think I'm going to use the files, or as I understand, you will play the video and then maybe I'll switch to the PDF for questions or something.
Yeah. First we will first we'll play the video and then you can talk on the PDF.
Okay.
Thank you.
So we will start, for example, 2 minutes later, or maybe less than. Okay, thank you.
Sadek,
Yes.
do you want to start?
Yes, of course. Okay. So
we don't have your voice.
Can you hear me?
I cannot hear you.
Yeah, we can.
Can you hear me?
No.
Yes, we
Yes.
all can.
Okay.
Yes.
So Saurabh, do you hear Sadek? Maybe. Oh, okay. So my speaker was off. Sorry, because I was
Okay.
into. So okay. Please start. Thank you.
So at the moment, can you hear me?
Yes.
Okay. So let me to start this session. This is the contributed talk provided by some participants. First contributed talk is given by András Kovács. He's going to talk about anomalous cold spot in the CMB, corroborating evidence from this and the possible solution. He provided the video, and after finish the video, maybe he answered the question by audience. Okay, please start.
In this presentation, I'm discussing new results from the dark energy survey in the context of anomalous cold spots in the CMB, aligned with the largest cosmic voids. And I'm also going to show you a possible solution to these anomalies, which, as it turns out, actually, and this is my main message today, is that it may also account for the other anomalies in cosmology, or at least it's shifting things to the right direction for the H0, S8, and Lyman alpha BAO tensions. And first of all, let me explain my main observable, which is the ISW effect, which says that in the presence of a dark energy component at low redshifts, the large-scale gravitational potentials decay, and in turn, secondary CMB anisotropies are imprinted on top of the primary CMB anisotropies. And what practically happens is that at 100 megaparsec scales, as photons traverse large-scale structures such as supervoid and superclusters, cold spots or hot spots are imprinted on the CMB map. And the details of the measured effect or the spots can constrain dark energy, being consistent with cosmological constant or more with some alternative model. This sounds nice, but actually the problem is that the signal appears to be too strong. So one effective approach to measure this kind of signal is to focus on the parts of the universe where these effects are expected to be the strongest, which means that you have to first identify superclusters and supervoids and then stack the CMB on their positions. And this is how the signal emerged from this SDSS dataset, but then right after this nice detection, it has been reported that the signal is like a factor of 4 to 5 higher than expected in ΛCDM. And this seems to be problematic. On the other hand, given the success of the ΛCDM model, and this is just a single measurement, the prevailing view was that this is a look elsewhere effect, let's say, which will go away when more data is taken. But surprisingly, this is not what happened. And with new data, almost completely independent data from the dark energy survey, we looked elsewhere. And actually, after showing that we are able to robustly identify the largest supervoids from photometric datasets using luminous red galaxies and estimating the expected signal from unbodied simulations, we did confirm the excess signal from this independent dataset. And here you can see the details of the measured profile from DES with orange, or in combination with reanalyzed BOSS DR12 dataset with the blue data points and error bars. And this, taken at face value, constitutes something like a 3 sigma anomaly for lambda CDM, and therefore I argue that it deserves some more attention and an explanation eventually. So what the data wants is somehow an enhanced effect from dark energy, which also is in principle aligned with the faster expansion at low redshift. So this seems to be like an interesting case to try to merge several different problems and attempting to solve them in a joint framework. So let's see what are the options. So first of all, one could enhance in principle the effects of dark energy by changing the matter density parameter or H0 itself, or the equational state of dark energy, and all of these changes, while not really supported by other data sets such as the CMB, they could do some significant changes to the expansion history. But on the other hand, as you can see on the left, they are not really useful in the case of the ISW anomalies, as the predicted signal compared to the CDM doesn't change too much. So we need something else. And in fact, we need definitely need something more radical to overcome this discrepancy. And for the purpose of this presentation, I call this class of models or family of models Model X. And what this Model X has to do for us is this really suppressed growth rate at low redshifts, which, in order to remain plausibly in consistency with the observed amount of matter density fluctuations, has to be compensated by a stronger gravitational growth at high redshifts. And if we look at the expansion history for the same model, then in order to end up with this consistently higher expansion rate at low redshift paired with the really suppressed growth, you also have to have some kind of compensation at higher redshifts, close to the peak of the quasar activity and star formation, where the expansion rate is slower, and this is in line with a more efficient gravitational growth. And the question, of course, is how do we create such a model? One option is to consider inhomogeneous cosmologies. And very briefly, the idea is the following. So if the universe is inhomogeneous, then different subregions with different matter density may expand at different rates. And what determines the global behavior of such a model universe in terms of expansion and growth is the representation of these different kinds of overdense and underdense subsets. And by definition, void regions increase their volume more efficiently, and therefore they become more and more represented in the cosmic volume average, which, according to these models, can be confused by a dark energy component at low redshift when nonlinear growth creates the very deep cosmic voids and the filamentary structure that we observe from surveys today. So this is the kind of the existing blueprint of this kind of inhomogeneous cosmologies, but the correct and proper implementation, I would say, is still missing. One thing which allows us to work in this context is the so-called Avera model, which is a modified embodied simulation framework. And there are some applications of it in the context of the ISW problem. On the plus side, on the right, I'm showing results from a paper I led last year, where we showed that this Avera model and this inhomogeneous cosmology approach can, in principle, explain the observed ISW anomaly, as you can see from the comparison of these models and the data points in clear conflict with the LCDM model. On the other hand, a more recent analysis of the DESI imaging survey also showed that in terms of the 2-point function, the 2-point cross correlation signal between the galaxy and temperature maps is over predicted in the sub-era model. So probably as it is, it cannot be the solution to these problems, but I would still argue that this is an interesting approach. And it is interesting because it can actually do more for us. For instance, it can incorporate, without changing any other parameters, the slower expansion rate at high redshifts measured from the Lyman alpha forest, as you can see here. And even more interestingly, the slightly different expansion history and growth history result in a slightly different dependence of the sigma 8 parameter on redshift, with, compared to LCDM, higher values at higher redshifts and eventually lower values at redshift 0, which has some relevance, I believe, in the problem of the S8 tension. And this brings me to my conclusions and the summary. And let me just highlight again that I think this problem is similar to the H-naught tension because in its detection, there is a sensitivity to direct or more indirect measurements. Also, it's not plausible to solve it within the LCDM model given other precise constraints, and also quick solutions do not work for the same reason, and they are also constrained. And yeah, I would just finally argue that these inhomogeneous cosmologies are promising but imperfect tools to consider, especially then to understand the BAO results in this framework. And with this, I thank you for your attention.
Thank you very much. Thank you for your presentation. Okay, we have time for some question and comment by audience. If please raise your hand. Any question?
I have a question.
Okay, please go ahead, Nima.
Okay, thank you, sir. Thank you, András. I have a question that, maybe I didn't get the point, because if you have a cold spot, it's kind of a spatial anomaly. But if you have a model to solve H-naught tension or sigma 8 tension, I assume that H-naught tension is not a problem with the direction of observation, no? So how did you say that they are related in your model?
Yeah, so it was in one of my slides that this approach, it's not really like a local void model, right? And what this like the core idea of this inhomogeneous cosmology suggests is that the properties are, you can consider them like an effective expansion rate and effective growth for like a modified simulation box, given that like overdensities or underdensities are represented. And once you create such a rescaled effective simulation box or model universe, then everywhere in that box you sort of have a unit. So how should I put this? So you could measure the like H-naught value at various locations on the universe, in this universe, and you will get, as an ensemble average, a higher value because this is like an emerging property of the model, not like a local effect. There can be, of course, local contribution to this. This is in the fundamentals of the idea, right? That you can have different expansions. But in terms of the H0 anomaly, the proposed solution is not that we are living in a void, but we are living in a universe dominated by voids.
Exactly, I agree. I mean, I agree with this point, but then I don't understand that then where is this cold spot? Because in principle, then you should produce more cold spot.
No, not necessarily, because you have what such an approach can basically give you is, so you generate the same, let's say, large-scale structure earlier, and then you have more expansion at low redshift. So you can, in principle, end up with the same large-scale structure, more or less. So your voids are not deeper or shallower, right? But the way they formed in this model is different, and therefore the strength of the cold spot becomes different, right? So it's like a historical difference, historical bias compared to the lambda CDM model. That's sort of the idea.
Okay, thank you.
Thank you. Any question?
If I can add,
Yes.
the lack of questions that.
So Paul has a question. Okay, go ahead, Paul, please.
Thanks. I just made a comment on the chat, which I just thought I would say that these cold spots might be an issue with the dust, or might be related to the dust emission, which I mentioned before by Wawrzyk. I'm not sure if you've looked at this possibility, since there doesn't seem to be a good model accounting for such cold spots. Wawrzyk did suggest that this could just be a natural consequence of the universe being more structured. So there are these voids, possibly even much bigger ones than the one we live in. And they would appear as cold spots completely naturally if the CMB actually is dust emission, so dust at cosmological distances between galaxies, which we know exists because it's measured, right? So this might be something to look or consider. You know.
I see. Well, one quick comment I can make is that there was a paper by, I think, Carlos Hernández Monteagudo, like 10 years ago, who looked into this anomaly, and basically the main point was that since the ISW signal is more sensitive to the gravitational potential, which varies at much larger scales than the density, and the kind of contaminations, extra radiation from dust that you mentioned is more correlated with the actual density field. In some really enhanced dust models, he found that like the shape of the signal it's not what's observed as an excess signal in lambda CDM because of this slight difference between density and the potential.
Yeah, one would have to look at the work of Wawrzyk, because I'm not sure what you just mentioned, what sort of calculations they did, but I think one has to try to step away from the LCDM constraint, which is irrelevant anyway because it's been falsified by much more than 5 sigma now, using very different tests, right? So one has to look at the possibility that the emission we see might be from a hot Big Bang in a different than lambda CDM model, or might be contributed by dust. Yeah, so I would try to do that, although nobody has done it yet. But given that we have these anomalies, we have to understand them, obviously. Yeah.
Okay, I'll have a look.
Yeah.
Thank you.
Thanks. Yeah.
Thank you. Okay, another question by Andriana. Okay, go ahead.
So I just wanted to mention, so it's very interesting, your model with the sort of enhanced structure, if I understand correctly. One thing I didn't fully understand is in what way exactly does this Avera model differ from lambda CDM? Because in lambda CDM, you also have overdense and underdense regions, and the voids would expand faster, if you like, than the overdense regions and come to dominate the volume. So I didn't understand how this differs from standard lambda CDM.
Yeah, well, I'm not the one who created the simulations or the model. I'm more the observer guy. But as I understand it, it's basically So this is a model without lambda, right? And what, as you could phrase it, is like emerging curvature. So you start with something like an Einstein of the universe at redshift 9, and then first you are more dominated by the overdensities, and eventually in the volume average you end up with the cosmic void. So there is and due to the volume averaging, you have this kind of funny difference. But you are right that in principle this is what happens in lambda CDM as well. So the voids can expand more, but yeah, it's not completely clear where the difference is amplified.
I think I read an article about this once, where it's the idea is to sort of in the Avera model is to simulate like different universes with different sort of matter density parameters to simulate different initial conditions. But one major problem with that approach is that the real world is kind of like that, or if it was governed by lambda C, it would look like that. But these mini universes would have tidal influences on each other. And this isn't taken into account, but in a large lambda CDM cosmos, so
I agree, and that's why I said it's this is motivated by the data. So something like this could explain my observations, but I'm not saying and I'm just thinking this further. What could imply?
Regarding the observations, that is perhaps the most secure aspect, like suggesting that because of the enhanced ISW signal, that you should find a way to enhance structure formation to explain it. That to me is a very natural path to follow. It's just I'm not sure this is the way to do it.
Okay.
We have to work more. Okay.
Thank you. Let's
thanks a lot.
Let's thanks the speaker again. Okay, and let's move on to the next speaker. Hello, can you hear me?
Hi. I can hear you.
Okay. So let's start with Marcel. He's going to talk about what new observations tell us about the planes of satellite galaxies, a persistent problem for lambda CDM cosmology. Please start. Thank you.
All right, let me see if my slides are somewhere. I think there they are. You can see that?
Yes.
Good. And let me just make sure you can see my pointer. Now you should be able to see that as well. Okay, thanks to the organizers for giving me this opportunity to talk here today about planes of satellite galaxies. We've heard about them a bit already. So just as a brief introduction. So there are a number of small-scale problems in lambda CDM cosmology that are quite famous. So missing satellites, forecast too big to fail. We heard Six talk yesterday about kind of a review of these and possible solutions. And many of these small-scale problems have in common that baryonic physics can address them, or at least can plausibly affect them, mostly because they have to do with the internal dynamics within subhalos. So in a sense, these problems are a potential failure of the simulations, but not the underlying cosmological model, or in other words, improved simulations can address them. Now, what I'm interested in is kind of trying to look at a more robust test of these cosmological simulations. So there's one shown here on the right, where you have a dark matter host halo, Milky Way size, and then all the subhalos around that. They are distributed almost randomly and an almost spherical distribution, and they also move in very chaotic manners. So there's not a lot of order. And what I'm interested in is looking at correlations on scales of hundreds of kiloparsecs within these systems of satellite galaxies around the host, which I think is a better test of the underlying model. Doing that, we've identified three quite popular and famous by now planes of satellite galaxies. One around the Milky Way, here seen edge-on, Milky Way's edge-on in the center. One around the Andromeda galaxy, found by Ibata et al. In a Nature paper 8 years ago. And you can color coded, we have the line of sight velocity. So you see that part of it is red shifted, the other half of it is blue shifted. So it looks like it's a rotating plane of satellite galaxies seen edge on from the Milky Way. And then we have a similar structure in Centaurus A, where we have a flattened distribution on the sky of the satellite galaxies. And we also see strong kinematic correlation. So what I'm going to talk about today is observational updates on these three. So over the last year, we've learned a bit more about each of them. So this will be really brief. And then I also compare each of these three to one common set of cosmological simulations, namely the elasticity TNG100 hydrodynamics one, as well as the dark matter only one, to see how likely is it that we find these weird structures in host analogs in those simulations. So let's start with the Milky Way. This is an all-sky plot, essentially showing galactic coordinates, but we don't plot positions, but instead orbital poles. Orbital poles are the directions of angular momentum, so kind of the normal vectors to the plane, the orbital planes of the satellite galaxies. We show the 11 classical satellite galaxies for which we had proper motion, so full 3D velocity information before Gaia. And you can see a strong clustering here in the center. Now these symbols here, these pink crosses and boxes, they are the normal vectors of the minor axis of the spatial distribution of the satellite galaxies. We see that the orbits, the orbital planes, align along these. So the normal vectors to the plane are pointing in the same direction as the angular momenta of most of the satellite galaxies. So that means the satellites orbit in the same sense around this host. And then there's Sculptor, which is 180 degrees off, which means it's also orbiting in the same plane, but in the opposite direction. So out of the 11 classical satellite galaxies, it looks like 7 or 8 of them are consistent with orbiting in the same direction. Now Gaia offered us an opportunity to get proper motions in a completely independent sense, completely independent data set. The previous ones were mostly based on Hubble Space Telescope observations. And Gaia showed exactly the same correlation. So we can combine the best available proper motions and get something like this. So there's not much of a difference, as you can see. You can flip back and forth. And main improvement is Carina has a much better constrained orbital pole now, and it aligns well with the spatial plane. We can quantify this by measuring kind of the clustering of these orbital poles. That's shown by these circles here, with this quantity. And we can look at how did this quantity evolve over time. So this is over the last 10, 12 years. And we see that it has steadily decreased. So this clustering became more and more pronounced, which is an effect of improved motion measurements. So as the observational errors were reduced, we kind of really figured out the underlying correlation, which is a strong sign that there is actually this underlying correlation and not just some chance alignment. As we get better data, the correlation becomes more pronounced, right? Now we can use this to, well, first look at the significance. So what's shown here is kind of, this is for the different circles, the size of these different circles, measuring the orbital correlation of the satellite galaxies. And the black line is what you expect for completely uncorrelated velocities. So you place the satellites at their observed positions, but the velocities are completely random and uncorrelated. And that's the median expectation. And these are the contours of 50, 90, 99% of realizations. And we see the observed line falls way below that. So the observed correlation is much tighter. It's extremely high significance, at least for standard astrophysics, maybe not high energy physics. So it's 99.95% significant. So this is not a chance alignment. In fact, if we consider the observed proper motion uncertainties we have right now, up to 7, the 7 most correlated satellite galaxies are as close as geometrically possible, given the uncertainties. So we couldn't even find a better correlation given their positions than we do. So this is pretty pronounced structure. So how does it compare to cosmological simulations? We select hosts of similar mass at the Milky Way, similar isolation criteria, and we do the same exercise. Now the contours are for dark matter only on the left and the hydrodynamics one on the right. We see that compared to the dashed line, which is the random velocities, there's a little bit more correlation. So it's a bit below that dashed line, but this is not sufficient. So the little bit more correlation you get in the MDCM simulations is not sufficient to really explain the extreme correlation you observe in the Milky Way satellites. And this is only looking at the orbital correlation. We also have to consider that the distribution is flattened spatially. If you combine both of those, no matter whether you look at 3, 4, 5, or 11 classical satellite galaxies, the frequency to find analogs drops below 0.1%. So it's a 1 in 1,000 exception with the current data. Now we can also look at Andromeda. This is the Andromeda satellite plane seen edge on from us. So this is the pandas footprint where most of the satellite galaxies were discovered. And so far we only knew the line of sight velocity. So we see the plane edge on and we know whether this part is approaching or receding from us. But there could be strong tangential velocities out of the plane. Now, last year, Son et al., I was not involved in that paper, measured the proper motion of these two galaxies with Hubble Space Telescope. So if we zoom in there, these are the two galaxies. This is the plane of satellite galaxies, and these are the directions of motion of these two satellites. They are perfectly consistent with moving along the plane in 3D as well. And so based on a method I developed in 2013, I can predict what proper motion measurements we would expect. So these blue contour shaded regions here, that's the proper motions I would predict for the satellite galaxies if they are orbiting along the satellite galaxy plane in the rotation sense inferred from the line of sight velocities. And indeed, both of these proper motions indicated by the orange circles are perfectly consistent with these predictions. We can again do the same exercise. We mock observe illustrious TNG100 hosts, which are similar to Andromeda. We apply the PANDAS footprint. We identify the most narrow plane of satellite galaxies in a similar way as done for the observations of Andromeda. And then we check how wide is it. So that's the horizontal axis here. It's very narrow in the observation and much wider in the simulations. And then we also look at how strongly correlated are the line of sight velocities. And that's, well, 13 out of 15 are correlated. So show the same line of sight velocity trend. That's also very rare in the simulations. So taking together these two criteria, we get that less than 0.14% of the simulated analogs are as correlated as observed. And that's even ignoring the proper motion information I just presented, because we ran out of statistics essentially. If we would add another criterion, it doesn't change anything because we already don't find any analogs. Now, last system, that's Centaurus A bit more distant. It's a massive elliptical galaxy. This work is led by Oliver Müller. I think he's in the audience. He also applied for a talk, and I unfortunately got chosen over him. So sorry for that. So Oliver has, well, we have obtained Muse data. He's analyzed that to get additional line of sight velocities. So we increased the sample size of 16 over to 28 satellite galaxies, and we still find this same line of sight velocity trend. And with the updated line of sight velocity data, we can again make a comparison between hydrodynamics on the right, on the left, dark matter only one, in illustrious TNG100, again mock observing the systems. We try to be conservative, so we only look at the line of sight velocities and the spatial flattening on as projected on the sky, because there are large uncertainties in the distances. And again, thinner planes on the left, more correlated velocities on the top. We have to be in these corners here to find a system which is as extreme as the observed one, and it doesn't happen that often, 0.2, 0.3% at most. So what could be possible explanations? Well, some people might be comfortable saying, yeah, these are exceptions. Maybe 1 in 1,000 cases are not that bad, but we have 3 of them for the 3 best studied systems. So why are we special? In a sense, we have to combine these unlikelinesses. So I want to address this in the future, of course, by studying additional samples of host galaxies and really building a statistical analysis of that in the nearby universe. Then there's this idea that host galaxy mergers could kind of create correlations in satellite galaxy systems. There's indication for past merger in Andromeda. There's strong indication that the elliptical galaxy in Centaurus A is a merger remnant where 2 major galaxies merge together, and this inch spiral might somehow create some correlation among the satellites because they fall in with these orbits, right? We've tested that. So that's Jamie Kanehisa's work. He was a master student working with me last year, and he looked at that also in illustrious TNG. He doesn't find any evidence for that. In fact, mergers, if anything, seem to destroy correlations in the satellite galaxy systems. Environment might play a role. That's an interesting aspect. So I checked that pairs of galaxies like the Milky Way and Andromeda in the local group, that doesn't seem to be sufficient, but there might be some relation to the larger scale structure around the local group. So looking at constrained cosmological simulations makes a lot of sense, because we see that the planes of satellites we know about, they have a certain preference to align with the larger scale structure around the local group and Centaurus. It's not a perfect alignment, but there's some hints and preferences that this goes the same way. And then the last possible explanation I want to mention that was also mentioned in Pawlow's talk is tidal dwarf galaxies. So if two galaxies merge, you might form actually new satellite galaxies. So in contrast to the merger scenario up here, these tidal dwarf galaxies would just be newly formed galaxies, whereas these here would be primordial galaxies brought in with the merger. Tidal dwarf galaxies should be free of dark matter. The observed galaxies seem to have high velocity dispersions, high dark matter contents. So this kind of only works if you are willing to change to modified gravity. And then, interestingly, it is more consistent because you would have a past encounter between the Milky Way and Andromeda, for example, in Mond, as shown by some papers. Nguyen is one of the people in the audience and busy asking questions all the time. So he can certainly tell you more about that as well. So if I still have a few minutes, let me just briefly say...
we are running out of time. Please finish soon. Thank you.
If you're interested, because in Joseph Silk's talk, he said that maybe the measuring cloud can explain all this. I'm very skeptical of that. I don't think we have the data for that yet. But just let me come to the conclusions. So we have planes of satellite galaxies, which are known around the Milky Way, Andromeda and Centaurus A. They are in strong tension with ΛCDM simulations. And I don't see a good way of improving these simulations. So hydrodynamic effects, for example, don't really change the positions and velocities of satellite galaxies on the scales of influence here. So that's why I think this is a serious issue and a serious problem we still have to find a solution to. Maybe we kind of have to go to more extreme ideas and study them in more detail at least. So thanks for your attention.
Thank you very much. Thank you for your interesting talk. We have time for a couple of questions by audience. If there is a question, please raise your hand to give a permission. Okay, I found. Okay, Indriana. Okay, go ahead, please.
I was wondering if you can show the slide regarding the Magellanic Clouds and why you think it doesn't work.
So it's not a new idea. So it was presented yesterday as kind of, okay, now we figure out that maybe the Magellanic Clouds have an effect on this. But actually, one of the first papers, Lindenberg, 1976, already speculated that the Magellanic Clouds might have brought in tidal debris. So that would also go into this tidal dwarf galaxy idea. But then also later on, Matthews et al., for example, showed that if you model an infall of a Magellanic Cloud with its own satellites, you would require it to orbit the Milky Way maybe 2 times or so to explain the plane of satellite galaxies. Because as you can see here, there's an all-sky plot, Milky Way along the equator. Plane of satellites is this great circle here. Magellanic Clouds are down there, but we have satellite galaxies on the opposite side of the Milky Way, which move along the plane. We have Leo 2 up here, which is at 4 times the distance from the Milky Way than the Magellanic Clouds, also quite an angle off, which moves along the plane. They cannot be stripped from Magellanic Clouds recently. There's just no way to get them there in time. And if you believe the proper motions and orbits for the Magellanic Clouds, they should be on first infall. So this scenario simply doesn't work out.
Can I ask another thing very briefly related to that? Like, is there also a problem that in this scenario, the satellites would preferentially be on radial orbits if the LMC fell in very recently, whereas most satellites are on tangentially biased orbits?
No. If I remember correctly, the angular momenta, say, of many of the satellite galaxies are in agreement with orbit similar to the Magellanic Clouds. So I don't think it should be super radial.
Okay, that depends when it fell in, but okay.
Well, it's falling in right now.
Okay, thank you very much. So let's thank the speaker again. Thank you very much. This is the last talk in this session, and thanks to all of you to attend in this session, and we should finish this part. And I think that I leave this rule to the one of the organizer to give some announcement if there is.
Hey. Thank you, Sadiq. Thank you very
Thank you
much.
very much.
Thank you very much. Thank you all the speakers. And okay, so let's do some local organizing job. Lloyd, can you hear me? Yes, so you do have...
Can you hear me?
Yes,
Okay.
yes. Okay, so first of all, thank you for joining us.
Yeah, my pleasure.
Okay, good. So I can see you perfectly. Do you want to share your screen or?
Yeah, that'd be great. So let's see.
Okay, so
I guess that's that icon.
Yes. Yes. Icon in the middle. At the middle, there's sharing. There's a monitor.
Yeah, so I see that, and I'm now setting up my preferences so that
Yes, please.
I'm following the instructions. Yeah.
Good.
So choose what you'd like to share. Application window. And Google's shoot, it's not letting me share yet. Let me start over. So I think there's something. I'm getting this. It's saying choose what you'd like to share, but then let's see. So maybe if I choose it, which is there. Okay.
Great. So
do you see a slide?
Yes, we do see. But do you want to go to full screen to check it if it's?
Yeah. Do you still see? Do you see my presenter view, or do you see just a slide?
No. We see the full screen mode, so it's
okay.
Yeah.
Looks correct. Okay.
Yes.
And let me just try advancing.
Yes.
Good. Okay.
Great.
Everything looks fine.
Yes. Thank you.
Yeah.
So.
Although I won't be able to see any of the chat while I'm presenting, the way this is working.
Yeah.
So if anybody.
But if anybody asks,
that's okay, right?
Yes, because usually people ask the questions at the end of the talk, and then or if it was anything, very important question, then I can ask you at the middle of the
Great.
talk. Yeah.
Great. Yeah. Please do.
Okay. Thank you very much.
Okay. Thanks, Nima.
Thank you. So see you very soon.
Okay.
And Levon, are you here? Maybe we can listen to music for a little bit and then coming back in 20 minutes. Less than 20 minutes. Puyan?
I will play it.
Okay, but can we... okay, so can I switch off Lloyd's screen?
Yeah, of course.
Okay.
Spaces involved. So I'm just going to summarize time. Sorry for running over a little bit. Gravitational waves can dissipate their energy to the primordial plasma, which creates spectral distortions. The dissipation may be weak, but because of that, it actually happens over a wide range of scales. And this means that spectral stations will one day be able to offer a unique or a complementary approach for new physics. And we invite everybody to test with their model of choice by downloading this package GW2SD. Thank you very much.
Thank you, Thomas. Great. Very nice slide. Thank you for presentation. Okay, great. So we have time for questions. If there are any, please raise your hand. Yes, Alex, please go ahead. You have the access to the mic.
Thanks. That was really interesting. Thanks for that. I just wanted to ask, like, could you tell the difference
Hi, Levon. Hello.
Hi, is that Nima?
Yes, it's me.
Sorry, I think I interrupted the nice music.
No.
Because
But,
I was trying
we are,
to find my file and then I clicked on it and it
yeah,
killed the music.
No, it's perfect. But we have 5 minutes. It's up to you. We can play a music for 3 minutes.
Yeah, sorry,
Yeah?
let's go back to music.
Okay, so
I see.
you just
Never mind. I see. Never mind. What do I need to do?
There is a 3 dots on top right, top left of the presentation. Now, then if you just exit or I close, or I can do it for you.
Okay, please do.
Okay.
Okay, thanks.
Thank you very much. So, Puyan, can you hear me?
Yeah, I can hear you.
Okay, and do you want to play that 3 minutes music before?
Yeah.
Okay, thank you. Okay, hello everybody. Levon, are you ready?
Yes.
Great. So welcome to the last session of the conference after 4 days. And for this session, we begin with Levon Pogosian talking about the Hubble tension and the magnetic universe. Levon, please.
Okay, thank you. Let me just make sure I can move the pointer.
For the
and enable mouse pointer. Can you
Yes.
see my pointer?
Yes, yes.
Okay. Okay, so hi everyone. I'd like to start by thanking the organizers and actually congratulating them for putting together such an interesting meeting. And also would like to thank all the previous speakers for giving really interesting talks. I really enjoyed my time this week listening to all the nice presentations. So as the title suggests, my talk is about the Hubble tension and what magnetic fields can do to maybe help with the Hubble tension, but also about some sort of lessons or insights we gained by working on this problem that go beyond the magnetic fields. So this is work with Karsten Judamzik and Gongbo Zhao that we did over the past year. Let me start with a plot that's made by Leonora Di Valentino and that's been shown at this meeting before. And one thing you could learn from analyzing sort of where all these data points come from, especially in a so-called early universe part where there is Planck and other data points and the BAO data points, they all have one thing in common, namely in the analysis that was used to analyze the CMB and the BAO data shown here, it was necessary to assume a model for recombination. So the sound horizon RD and the redshift of recombination were derived using a model. And one could ask whether the tension persists if you kind of abandon your model of recombination. With CMB, it's kind of tricky because you need recombination theory to calculate both the redshift of last scattering and also the sound speed at last scattering. But with the BAO, you know the redshift because you measure the redshifts of the galaxies, but the sound speed is still unknown. So you could ask, maybe we can learn something from the BAO by treating the speed of the sound, your standard ruler, as an independent parameter. So that's what we did in a recent paper. We treat the sound horizon RD as an independent parameter and look at the latest BAO data, which includes the DR16 EBOS data and all other usual data points that people include into their BAO analysis. And if you look at what BAO constrains, it's this angular scale or the ratio between the sound horizon at decoupling and the distance to a redshift at which you measure your BAO. And in a flat lambda CDM universe, it depends only on RD, H, and omega meta. And you can see that by itself, BAO can only constrain omega meta and RD times H. So it constrains a combination of RDH. And this is what you see in a bottom left plot. Adding supernovae helps a little bit because supernovae can constrain the capital omega meta. But you cannot disentangle RD and H by using BAO alone. And that's been mentioned prominently at this meeting before. Now, if, on the other hand, you provide some kind of knowledge about the actual meta density, namely little omega meta, that actually breaks the degeneracy between RD and H. And you can see it nicely in this equation, which is the same equation, but rewritten in terms of the little omega meta. Now you see that if you have BAO at different redshifts, you will break the degeneracy between RD and H. Then you could ask, where would such a measurement of little omega meta could come from? And there are sort of two directions you could pursue here. One is to combine BAO with measurements that do not strongly or practically weakly dependent on recombination, such as CMB lensing or galaxy lensing. Such measurements do depend on omega meta H squared, but don't depend on recombination. Cosmic chronometers is another idea. You could think of including them. Or you could do a consistency test. So you could take your favorite omega matter h squared, such as the one measured by Planck using ΛCDM model, and use it as a prior and ask, does BAO then give me the same h naught as I would get from Planck? And these plots here show both methods. And you can see there is a broad consistency independent of which method you use. Either you use a consistency test using a prior on omega matter or combine it with other data. So you get a broad distribution. You get something like 69.5 plus minus 1.8 for the Hubble constant. So there is no real tension with either Planck or shoes. There is a bit of a tension, but we wouldn't have a conference about it if it was just that. So BAO by itself, without a model of recombination, is not in tension. In the future, this kind of approaches can provide a really stringent test of the Planck constraint on h naught. Namely, if you just take the Planck prior on omega matter and apply it to future DAISY BAO data, you can get a measurement of h naught with an accuracy of 0.3, which is what you see in this paper. So the Planck accuracy, Planck uncertainty for comparison is something like 0.5, 0.6. So this would definitely tell you if there is a consistency between the BAO and Planck or not. So that was sort of a motivational perspective on looking into something at recombination as a way of solving the Hubble tension. Now, what sort of things can help with that? And I'm going to be a little bit controversial and maybe a little bit biased by saying that there are two classes of proposals here. There are many models proposed that aim to modify something at the before or around recombination and solve the Hubble tension. And there is really nice work done there, and I follow that work, and I did some of that work myself, trying different types of models. But then there are the primordial magnetic fields, and what distinguishes them is that there was no sort of special design involved. This was not invented to solve the Hubble tension. The work that led to this realization that they can help was done 10 years ago, so we just applied it. Now, to give you, again, some kind of a perspective and context for what I'm going to say, let me briefly review sort of the state of the art in cosmological magnetic fields. And for a more comprehensive review, I highly recommend this paper, recent review by Tanmay Vachaspati, which is 25 pages long, but contains everything you need to know about cosmological magnetic fields, or at least what a cosmologist needs to know about magnetic fields. So magnetic fields are an old problem in cosmology and in astrophysics. We have observed micro-Gauss fields in pretty much every galaxy or in a cluster of galaxies in which such a measurement was possible. And the question is why it's such a universal number. Why is it always like 1 to 10 micro-Gauss? And the dogma that, if you ask a random astrophysicist where did they come from, they would say it's a dynamo mechanism, which is, of course, a legitimate answer. Dynamo does amplify magnetic fields from a small seed. But then the question would be, well, why would there be micro-Gauss fields in galaxies that don't necessarily have enough time to turn sort of sufficient number of times to generate a magnetic field through a dynamo, such as in very high redshift young galaxies? So there is a bit of a puzzle, and also this number is very universal across young galaxies, old galaxies, elliptical galaxies, spiral galaxies, sort of a bit of a puzzle there. So you could then speculate that magnetic field was already there in the primordial plasma and got compressed together with matter during structure formation, and so magnetic fields that were already there got compressed and formed these micro-Gauss fields with maybe a little bit of help from dynamo. Now that's just a nice story, but there is recently additional evidence that came from blazars, from gamma ray astronomy provided by Fermi satellite, and it's because they claim actually a lower bound on the magnetic field. I thought it's important that I spend a couple of minutes sort of explaining that claim. So I'm referring to a paper that's now more than 10 years old, where they claimed a detection or a lower bound of something like 10 to minus 16 Gauss of magnetic fields correlated on megaparsec scale. So we're talking cosmological scale fields in intergalactic space. And while all the details of this analysis are rather complicated, there's a lot of gastrophysics happening here, the basic principle is quite simple. And the idea is that you have this TeV energy gamma rays called blazars that shoot at you with some periodicity. So as they travel through space, and they do travel some cosmological distances of order 100 megaparsec, let's say, before they hit another photon, like a loose extragalactic background light photon, which would have an energy of order 1 or a few electron volts. And the center of mass energy of that collision would be large enough to produce an electron-positron pair. So this E plus and E minus would continue because they got hit, they were produced in such a high energy, by such a high energy gamma ray, they would continue roughly in the same direction as the original gamma ray, and eventually interact with some CMB photons and upscatter them to higher energy photons, typically of order GeV. So because of this upscatter, you expect to see GeV level gamma ray halos around TeV blazars. And what happens is that you don't, or at least for many of these blazars, there is no halo. And one explanation is that there is a magnetic field that diverges the trajectories, deflects the trajectories of the electron and positron, so that this GeV gamma rays are deflected out of your line of sight. And this is the basic sort of idea behind this claim. And as I said, there is a lot of modeling and there are some open questions, but this claim is 10 years old, and there are subsequent works that sort of contributed to this lower bound. So this is certainly not dead. More recently, there was an observation by LOFA of synchrotron emission from sort of an extended ridge connecting two merging galaxy clusters. The extent of that ridge is about from 3 to 10 megaparsecs. And synchrotron emissions suggest that there are both relativistic electrons and magnetic field present. And they're modeling, I mean, at least in a paper, they claim that they tried various models to explain this, and the best model that fits is that of a primordial magnetic field. So astrophysical magnetic fields fail to explain this emission. So that's sort of the observational side. And on the theory side, you expect to produce some magnetic fields in the early universe. It's not a question whether you produce them or not, but whether they would be of sufficient level to be relevant for observational cosmology. And that's an open question. And if, of course, if you detect anything that suggests with some certainty that they are primordial magnetic fields, it would be a huge discovery for our understanding of the early universe, because now we would have to come up with theories to produce them. So let me give you all you need to know for this talk as far as the background on stochastic primordial magnetic fields. So they are indeed stochastic. We're not talking about some uniform magnetic fields that have a certain direction across the universe, breaking the isotropy. This is a stochastic field, so both the amplitude and the direction of the magnetic field fluctuates from place to place. Now, they were produced presumably at some very early time in the universe, could be during inflation, could be in something like the electroweak phase transition after the inflation ended. Once produced, they would remain frozen in plasma, and because plasma is highly conducting, it will preserve the magnetic fields in this frozen state. And magnetic fields would expand like any other radiation. So the density in a magnetic field energy would go down as 1 over scale factor to the 4th, or the strength of the magnetic fields goes as 1 over a squared. And depending on how they were produced, you expect a different power spectrum for the magnetic field. So if they're produced in a phase transition, most of the magnetic field energy would be at the scale of the horizon at the time of the phase transition. So later on, you would have a magnetic field spectrum sharply peaked at the smallest scale that it exists. But if it's produced in inflation, there is more modeling freedom, and the simplest, earliest models of sort of magnetic field producing inflation, such as that by Mike Turner and Bharadwaj from late 80s and early 90s, they predicted scale invariant magnetic fields. This is a plot from Tanmay Vachaspati's review, which in a very sort of broad, non-exact, schematic way summarizes the current state of what we know about cosmological magnetic fields. So on a y-axis, it's B lambda, where you can think of it as something like magnetic field on a particular Fourier scale, inverse of which is lambda. So it's a magnetic field strength or magnetic field power on a given scale. And the x-axis is that scale. And you can see there are upper bounds coming from the BBN, from Faraday rotation, from CMB anisotropies. The golden square here is the amount of magnetic field you would need to produce galactic and cluster magnetic fields with minimal dynamo. So you need something around 10 to minus 10, 10 to minus 11 Gauss at 1 kiloparsec scale to get them through just compression. And then you see these lower bounds from blazars that I described before. And the two lines are theoretical predictions. So the dotted line is the distribution of power if you have a scale invariant field. So, and the dashed line is what you would expect in a typical phase transition scenario, such as the electroweak phase transition. The two lines are normalized so that they pass through this golden square. And because the exact amplitude for the theoretical prediction does not exist, it's still model dependent. So now that I motivated that magnetic fields are something you should think about, at least from time to time, how do they help with the Hubble tension? So in very brief 2 sentences, what happens is that if you have magnetic fields just before recombination, then they start inducing baryon inhomogeneities on small scales. By small, one means scales below the photon mean free path. So something like 1 kiloparsec scale. And those inhomogeneities have the effect of speeding up the recombination. And as you would know now, after hearing so many talks about the Hubble tension, if the recombination happens or ends earlier, then the sound horizon at recombination is smaller, and that helps to get a larger H naught from measurements of CMB. And I want to explain this in a little bit more detail by showing you the key equation here. So this is the earlier equation governing the flows and forces on baryons at the time of recombination. You see on the right-hand side is the Lorentz force, which has this part, which the gradient of B squared, that pushes baryons towards regions of low magnetic energy density. Then you have the friction term. So at that epoch, magnetic fields are not turbulent. They are highly damped. So it's a viscous plasma. And then you have the pressure term with the speed of sound being in 2 regimes, depending on what scales you look at the plasma. So on scales larger than or comparable than the photon mean free path, it's your usual tight coupled fluid that we people working on CMB are well familiar with. But if you look at length scales well below the photon mean free path, such as 1 kiloparsec, the baryons behave like a viscous compressible gas with very small speed of sound. And on those scales, baryons are free to cluster in response to this force by the baryons. The impact of that is that now your electron density becomes inhomogeneous, or free charge density is inhomogeneous, and that affects this recombination rate. The key here is that you have an n squared sitting in the equation, which is a nonlinear term. And as we well know, when we average this over many parts of the universe, the equation is local, so you average it over an inhomogeneous distribution. You know that the average of a square is always bigger than the square of an average. And that means that the term responsible for actually recombining is larger, therefore making the derivative more negative. So the recombination proceeds faster. And this was pointed out first by Yadamzik and Tomabel in 2011, and where they have shown both that the recombination indeed proceeds more efficiently and that it impacts the CMB peaks, pushing them to the right. So, of course, at that time, there was no Hubble tension, so that was the end of the story. They just commented that this would provide pretty strong constraints on primordial magnetic fields. No, with the Hubble tension becoming a big deal, we decided, so Karsten and I decided to return to this idea and see what it can do. So here is how we model this effect. We take exactly the same model that Yadamzik and Abel took in 2011, and Karsten actually implemented it in camp at that time, so we did not have to write the new code. So that model has one additional parameter, which is called the baryon clumping, defined in this way. And it's important to emphasize that the distribution is not Gaussian, and strictly speaking, this clumping parameter does not define all of the distribution of baryons. And the shape of this distribution matters. And so just to see to what extent it makes a difference, we tried, in addition to the distribution of baryons, distribution function assumed by Yadamzik and Abel in 2011, we tried a different one just to see the impact. And then we fit it to all the available data, like the Planck data that exist in CosmoMC, and also the recent determinations of the Hubble constant, and also other data. And first, let me just comment on the CMB part alone. So what happens when you fit to Planck only? You don't see a detection of clumping, but you see a degeneracy direction opening up, where you see that now CMB can be consistent with a larger H0 at the cost of increasing clumping or the strength of the magnetic field. But there is no preference if you just take a CMB alone. If you now include the local measurements into consideration, like the 3 measurements I mentioned, including shoes, with shoes clearly dominating, I could have just including the shoes measurement alone, then you get a clear detection of clumping and a definitive shift of H0 to a larger value, something like 71. And you could ask, well, does it make the fit to CMB worse? Because CMB by itself does not prefer a non-zero clumping. The answer to that is no. CMB fit gets slightly worse, but not at any level that you would worry about. If you look at a number like probability to exceed, the PTE for lambda CDM is something like 20% for the Planck best fit lambda CDM. In this case, for the best fit magnetic model, the PTE is 17%. So a degradation from 20% to 17% is not something you would consider worsening of the fit. And this is how it looks if you look at just the probability distribution for the H0, a clear detection of clumping and a shift in H0. This is just fitting to Planck plus the local measurements of the Hubble constant. And this is what happens to the other tension. So that was kind of a little bit of a surprise, although in hindsight we should have expected it, that as a byproduct it also solves the S8 tension, because a larger H0 helps with lowering S8, because in our model the physical matter density omega matter H squared stays the same. It's the same best fit in lambda CDM and in our best fit model. So if you have the same omega matter H squared and the larger H, you get a smaller omega matter and therefore a smaller S8. And this is how joint constraint on S8 and H0 looks when you combine all of the data. And here the best fit H0 shifts a little bit to the left, so the best fit is now more like at 70.5. And the reason for this worsening of worsening of the tension, if you wish, is because we included the BAO data. And that's a broader problem than just the one with the primordial magnetic fields. And that's something that was mentioned in a couple of talks before. So I decided I'll go over this in a little bit of detail. So as I mentioned, as a result of working on it, we kind of gained a bit of a broader perspective on the Hubble tension. Namely, if you look at this RDH node diagram and think of RD as an independent parameter, then in lambda CDM, you have three free parameters. It's RD, H, and omega matter H squared. Then if you fix RD, then any measurement of a BAO like feature at a given redshift or the CMB peaks gives you a line in this plane. So the red line is the one from the measurement of CMB theta at the fixed omega matter H squared, like the best fit lambda CDM value of 0.143. So these other lines that are plotted are a representative plot of BAO lines at redshifts 0.5 and 1.5. So you see that lines at different redshifts go at different angles. And the blue band is all of the BAO data marginalized over omega matter H squared. So that's the same constraints I showed before. Now, if you try to solve the Hubble tension, right, you try to lower your RD, and you move along different lines. So if you're trying to solve it in terms of moving the CMB peaks in the right direction, so you move along the red line, you lower RD, and that quickly takes you out of the BAO band. So to make the red line consistent with choose, you have to be outside the blue line, which is the BAO. The way to reconcile CMB with a smaller RD and at the same time, if you choose, you have to increase omega matter H squared. So you can move the CMB lines into an overlap region between BAO and choose by increasing omega matter H squared, which is what you see in this plot. So to get a perfect agreement, you need something like 0.167, which is significantly larger than 0.143. And that generally leads to more trouble with the SA tension. So you move further away from this DES constraint that I show on the right-hand plot. So this is a sort of very simple argument that it's not easy to solve the Hubble tension by just lowering the H naught, even if you happen to get a perfect fit to CMB, polarization, all the other stuff, which is, of course, by itself non-trivial. I'm starting to wrap up. So magnetic fields can help with the Hubble tension to a certain extent. They can raise the fit you get to CMB and BO together to something like 70, which would help, I think, with H naught tension quite a bit. And it eliminates the SA tension. The amount of clumping you need implies magnetic fields of strength of order 0.05 to 0.1 nanogauss. So that number is kind of special. Let me go back to the plot I showed before. You see this golden square. So it's exactly where clumping points us. So you shouldn't feel too guilty about getting excited about this. This is quite a nice coincidence, and it certainly deserves further work. Another thing to say about this model that it's quite testable, highly falsifiable. It's just a matter of time before it will be ruled out or confirmed. And future observations over a broad range of scales and redshifts where magnetic fields are relevant would be able to detect if magnetic fields are indeed present in primordial plasma at this level. So most prominently, I would mention sort of very high LCL measurements. You could look at CMB spectral distortions that we heard a very nice talk earlier about that. So magnetic fields would dump energy into the plasma and create both mu and Y type distortions that would be within the range of Pixie type experiments. And there are other like blazars. More blazar data would produce stronger sort of lower limits or no limit, sort of constraints on magnetic field. So there's a lot of tests you can think of to test, because we have a very specific number. It's something like 0.05 nanogauss at 1 kiloparsec, and that's a firm prediction. So you can look for the implications of that. But before you do that, what's missing at the moment is a detailed prediction for the shape of the probability distribution functions for the baryons. And that's something that will be determined. So we're working on it right now, doing MHD simulations of primordial magnetic fields at the time of recombination, and there will be an answer. So then once we have a firm prediction, you can go after all the other things with much more certainty. And that brings me to my conclusions. As I said in the beginning, the Hubble tension, the way I see it, points at a potentially missing ingredient in the physics of recombination, unless it's just a systematic of some sort and the whole thing will go away. But we've heard so many talks, it's not something very simple that will just go away. Like the case is becoming more convincing. And that missing ingredient could easily be the primordial magnetic fields, because their existence was expected for other reasons. And magnetic fields can help raise the value of H0 that you get from CMB and BEO to something like 70. And this doesn't go all the way to the range suggested by Shoes, but that may turn out to be all we need, because the tension, if H0 is 70, I mean, the tension is not as significant as it is now. So that's the end of my talk. Thank you very much for the attention. Thanks again to all the organizers.
Thank you, Levon, and people are thanking you virtually in the chat box.
Thank you.
Yes. So we have enough time for some questions. If there's, yes, Adam, please.
Lovely talk. I really enjoyed it very much, and I learned a lot.
Thank you.
My question is, if you sort of flip it around, I mean, in standard analyses of CMB data, people assume magnetic fields are zero and the clumping is zero.
Yes.
You know, I guess what I would say is that well motivated? Is that something that is justified? I mean, I spent a long time in my early career with people telling me the cosmological constant was zero, and that was never really that well motivated. It was just simpler. So is it fair to say the statement of magnetic fields are zero, is that, one quite plausible possibility, or is it, really, we have no reason to set this free parameter to zero to begin with?
Yeah, very nice question, worth asking. I would say a zero is completely excluded, because some magnetic fields must be present, but they could be easily much lower than the level required for them to be cosmologically relevant.
Mm-hmm.
So in a diagram that I copied from Tanmei's review, this golden square is normalized. So it's put there as what would be needed to explain all the galactic and cluster fields with practically no dynamo. But if you start going into sort of more astrophysical details and allow for more dynamos, some other mechanisms, it might move a little bit more down. And then such weaker magnetic fields would not necessarily be cosmologically relevant. So I wouldn't go as far as requiring people to include them into their codes, but I mean, and another thing to consider is that it's a little bit premature to do so, because as I mentioned, we need a firmer model for this effect for it to be like beyond doubt, if you.
Mm-hmm. Mm-hmm. Thank you.
Mm-hmm.
And Jens, please. Jens? I cannot hear you. I don't know if... Yes. Yes. Please go ahead, Jens.
Hello?
Do you hear Jens? Jens.
Quick question concerning Big Bang nucleosynthesis. I guess there wouldn't be any effect, right?
No, so as you see from the diagram, I don't know if you can see the slide I'm showing. The Big Bang nucleosynthesis constrains the contribution of magnetic fields to the total amount of radiation you're allowed to have, and it's much weaker. So we are well below those bounds.
Okay, good. And now it's time for Alex.
Really interesting talk. I just want to ask about the implied additional clumping of the baryons. Are there any observational signatures of that, perhaps either in early galaxy formation or in 21 centimeter in the dark ages or something like that?
Yeah, that's a very good question to ask. I cannot say they aren't. So one thing to realize, this inhomogeneities do not grow indefinitely. They reach order 1, so little delta rho by rho gets to about 1, order 1, and then that's it. So it's not a very strong effect, and it only affects the baryons. We thought a lot about it, and Karsten, my collaborator Karsten Damzig, with Tom Abel, very strong on as far as aiding structure formation. But 21 centimeter, again, sort of back of the envelope estimates that we thought of did not lead us to think that there could be a significant effect, but I wouldn't claim to have it.
Great. So Yasha? Yasha?
Yeah, hi. Can you hear me?
Yes.
Yes.
Yes. Thanks a lot, Levon, for the beautiful talk. So I mean, I have a question. Maybe you have already answered that. My apologies if you have done that. Maybe I missed it. So my question is about this dynamo mechanism thing. So I mean, how much? So basically, how much do we know about that, or how much freedom do we have in that? I'm asking. I guess I'm asking this because imagine that we know exactly how much this thing will enhance the magnetic field. Then in that case, we should know exactly what the seed should be. And then, I mean, we don't really have freedom to play with that. So it's just my question is how much freedom we have in this mechanism.
Yeah, you could be pushing me to the limits of my expertise, asking me questions about sort of galactic dynamos, but I can tell you how I see it. So let's say if we take the Milky Way, it turned around 40 times in its lifetime, and that is enough to produce the micro-Gauss level fields we see in the Milky Way from a very tiny seed. So the seed you would need for an old galaxy like ours is something like, I've got 10 to minus 30 Gauss, very tiny. I'm just putting it out of my head, but extremely tiny, much lower than here. But then if you look at this high redshift, so proto-galaxies, where you also see micro-Gauss fields, they would have only maybe time to turn 5 times at most. And you see again a micro-Gauss field. So in that case, you would need a seed which is more like 10 to minus 14 Gauss. So it's kind of strange that you see the same number, independent of how many times the galaxy had time to turn as an initial condition, and it turns 40 times. Why wouldn't it be a much bigger number than micro-Gauss, right? Exactly. And I think, I'm not an expert on this, but I think there is some saturation taking place. Namely, there is a feedback mechanism as well, where you cannot just amplify the magnetic field indefinitely. At some point, it starts also slowing down the dynamo itself.
So basically,
there is a saturation effect. But again, as I said, you're pushing me to the limits of my expertise here.
No, thanks a lot. No, I just wanted to know. So basically, the theory is not completely. I mean, it's not completely known. So there are basically things that we don't know.
I mean, there are
about,
people
right?
who know a lot about this. I'm not going to say the theory is. There are open questions, of course. Yeah.
Okay. Thanks a lot.
Thank you. And Jens?
Sorry, I hope it's working now.
Yes.
Yes.
Thanks a lot for this nice talk. You mentioned the n square effect and, of course, the enhancement of the recombination rate in that way. How much is the role of heating mechanism? So the dissipation of the magnetic field lead to changes in the cooling rates of electrons. So what is the relevance of the temperature of the electrons, how they change to these magnetic fields? What is your feeling for that? And are you planning to include that?
Yeah, I remember discussing this with Karsten, possibly with you or one of your graduate students or postdocs. We discussed this a little bit, and the estimate at the time was that the kind of magnetic fields you need to produce an observable heating effect would have to be larger. So these magnetic fields are weak enough that their contribution to heating to be included in a recombination sort of equation can be neglected. So we don't include it in our equations because you need.
But that is for the average. So
if I remember,
how about?
That's a good question. So if it's fluctuating, then locally it could be larger. Is that what you're saying?
Exactly. Yeah.
Yeah. Yeah, that's a good question. I think it's definitely worth looking at it in detail, but we haven't yet. We looked at sort of the kind of numbers we got from maybe your papers and Kunze and Komatsu, where they looked at sort of what sort of strength magnetic fields you need to have impact on heating, and they were generally larger than 0.05 nilogauss.
Yeah, very good. Thank you.
Yeah.
Thank you very much. Is there any other question? Okay. Pavel, do you have a question? I see that your hand is raised, or it's from the previous one. Okay, good. So there is no more question. Let's thank Levon again. Thank you very much, Levon. Thank you.
Yeah, I'm trying to close my file. Just,
yes. Perfect. Thank you. And our next speaker is Lloyd Knox. Lloyd? Yes.
Okay, people can hear me and see.
Yes.
Great.
Yes.
Okay. Thank you very much for inviting me here. Thanks for organizing this conference. I really found it revitalizing. It's actually helped me to understand how much I benefit from conferences like this, usually in person. I found it revitalizing. It's been really helpful to me. I've learned a lot, so thank you very much. I also understand that now in Tehran it is not only late, but it's late on Thursday. So thank you for being here, even though it is the beginning of the weekend.
Okay, thank you. Yes, it's very late. Yeah, and I should add that today was a holiday in Iran.
Oh my goodness. Okay.
Yes. Yeah. Okay. So
all right.
Thank you very much for accepting our invitation, and we can start.
Okay.
Yeah, please go ahead.
Great. So here's my title: Can additional light relics restore cosmic concordance? And just to preview the answer, I am following the usual rule here with titles that are questions. If I had to answer this in one word, the answer would be no. But I think it's very worth exploring the physics of why. And so I'm going to be talking about this work that is not yet published. It's work done in collaboration with my graduate student, Fei Ge, and Francis-Jan Siracine. So why light relics? So I think there's two important reasons. One is that they leave key observables invariant by allowing movement in what we're calling the BAO scaling direction. So once you can allow the radiation density to move, then, which you can by adding in light relics, then you can scale up without changing the shape of H of Z. And of course that boosts H0, and it also leaves the number of important observables unchanged. So it opens up this degeneracy direction. There's a particle physics reason too, which is that theories with additional light relics are commonplace. In fact, theorists are often struggling to avoid additional light relics to comply with cosmological bounds. So that's quite in contrast to other proposed solutions to the Hubble constant problem. So why aren't light relics a solution? Well, first of all, there are effects that impact observables that are not BAO scaling invariant. So one of these is photon diffusion. Another is free streaming of the relativistic particles and the associated rapid potential decay. This rapid potential decay affects the amplitude and the phase of acoustic oscillations in the plasma. However, there are ways we can mitigate these effects. And so introducing those, maybe we can then answer our question in the affirmative. Yes, additional light relics can restore cosmic concordance. So here's the outline. I want to define this BAO scaling. We'll look at these effects that break BAO scaling invariance, these two I've mentioned. We'll look at the mitigation of these effects and how well they work. And then, because that they basically, we've been surprised at how the limits on how well they can work in terms of boosting H0. We then have figured out that there's another important effect going on that impacts CMB polarization that I'll be telling you about. So what is this BAO scaling? So it's a shift in the parameter space that just scales up H of Z everywhere. And such a shift will leave these two BAO observables invariant. And so the angular size of the sound horizon and then the redshift space separation of one co-moving sound horizon. So both of these are invariant, at least if in the approximation that, let's see, can people see my cursor here? Maybe not.
We don't see actually.
Okay, shoot. Okay, so I will just not rely on that. So in this expression for this sound horizon, if we're not fundamentally changing recombination, then these things remain invariant as the sound horizon is going like 1 over alpha, and the angular diameter distance is also going like 1 over alpha, and these cancel out. And so these are both for galactic BAO and also for the angular size of the sound horizon on the last scattering surface. So basically, in following the scaling direction, we're scaling up this whole triangle on the bottom and leaving the angles invariant. But in order to exploit that BAO scaling, we require additional light relics, because to keep the H of Z fixed as H0 increases, we need to boost all 3 types of densities. And if we break apart the matter component and the radiation component here, this rho XLR is the density in extra light relics. And so this NF parameter controls rho XLR. And as delta NF increases along the scaling direction, we increase rho C0, the cold dark matter density and the cosmological constant, to preserve the shape of H of Z. So that's the BAO scaling direction. and the addition of light relics allows us to exploit it. So let's look at these effects, photon diffusion and free streaming. So a photon initially has a very small mean free path as it's in the primordial plasma with a high electron density, and eventually the electron density drops and the mean free path increases, and the photon diffuses some before taking its last scatter before heading our way. So this typical distance that a photon diffuses before last scattering is this diffusion length, and it is not a BAO scaling invariant, right? It's RD squared that goes like 1/h. Since this is a random walk process, the square of the distance is going up like time rather than going linearly with time. And so this diffusion angle is not BAO scaling invariant. And you can see this in this case, just show you, simulated maps where we're going to switch from NF equals 1 to NF equals 10 along the scaling direction. So the angular size of the sound horizon won't change. So here's NF equals 1 case, and then if we go to NF equals 10 along the scaling direction, the diffusion angle increases, and you see the suppression of the small scale power. That's an observable consequence of the diffusion effect. We can see that on spectra. Here I'm showing a spectrum of the temperature power spectrum, but with the damping effect for the n equals 3 case, n effective equals 3, or here what we call n nu equals 3 case, folded out. So we're correcting all the spectra for the damping expected at the NF equals 3 case, just to better see these spectra. And you can see here, right, as we're increasing the number of neutrino species, we're increasing the amount of damping. These models are also all along, these 3 models are all related to each other by the scaling direction, and the way we've varied parameters between these models. Now, if we also vary a parameter to keep the damping scale fixed as well, we see a remaining effect, which is largely an amplitude difference. And this comes from the free streaming of the neutrinos, where since the neutrinos can free stream at the speed of light, the potentials decay rapidly. Without this effect, the decay of potentials that happens at horizon crossing is nearly resonant, and that this nearly resonant effect drives up the amplitudes of the oscillators. But including this free streaming effect makes the potential decay more rapid, and in fact further away from resonant, and so actually reduces the amplitude of the oscillation. So you see here that as we're increasing the number of neutrino species, the amplitude is going down. We can compensate for that by adjusting the amplitude of the primordial fluctuations. And if we do that to just normalize these to the 4th peak, then what's left is a very subtle effect from a phase shift in the temporal phase shift in the acoustic oscillations, which ends up shifting the locations of the peak. So this very subtle effect that nevertheless can be teased out of the data is there and contributes to constraints on light relics. But there's ways to mitigate these effects that I'll go into now. So if you really want to preserve light relics, and it's worth trying for the reasons I gave at the beginning, particularly in particular that the presence of additional light relics is not a surprising thing from a particle physics perspective. So to compensate for photon diffusion, we can let the fraction of helium vary. There's changing the amount of helium at fixed baryon to photon ratio changes the number density of electrons through recombination, and certainly impacts the this diffusion angle. And for the free streaming effects, there's nothing to prevent us from having the additional light relics be a fluid. So strongly interacting particles behaving like a fluid, and that will eliminate the free streaming and eliminate these effects I just discussed. So how well do these work? I had a student investigating this, and we were dealing with our surprise at how well it does not work when this paper came out. So I can show you these results. That let's look first, lambda CDM plus NF, 67.4 plus or minus 1.1. And if we introduce this extra freedom, so we make it we allow for there to be a fluid component. So this is a free streaming fraction here. We allow for a fraction of these effective degrees of freedom to be free streaming, and some of them to be fluid. Then we go to here, not much change at all. And then even adding this additional parameter, we're only opening it up a little bit, right? So we've added 2 new free parameters, and we've increased the errors by just 40%. Not a huge change. And the question we had was why? Why isn't this opening up things more? And so to address that, let's look at just the constraints from just temperature. Before that was including temperature and polarization. So here's what we have for temperature in these 4 different model spaces. And we see that the addition of helium is making a big difference here. And this is, could go a long way towards reconciling with this is the R19 result of the Rees et al. 2019 result for the Hubble constant. But if we add in polarization, these really tighten up significantly. So particularly everything except for this last category. And so we wanted to know why. Why is polarization having such a significant impact on these model spaces? So let me go into that, and let me remind you about how polarization is generated from unpolarized radiation. And here's this cartoon from Hu and White, where you have radiation coming in from the left that is unpolarized, but it's brighter than the radiation that's coming in from above. And as it scatters off the electron, only one of those polarization states can scatter in this particular direction, which we'll assume is the direction we're observing from. And likewise, with the radiation that's coming in from above, only one of those polarization states can scatter into the line of sight to the observer. And the net result then is polarized radiation. So in general, what you need is a quadrupole pattern incident on an electron to create polarized light from unpolarized light. So we need quadrupole moments, and these are generated by free streaming. So if you're in a plasma and the mean free path is very short, you're not going to see a quadrupole moment because all of the radiation you're seeing is coming from right near you where the temperature is the same. So you need some free streaming to generate quadrupole moments. So and this is heavily suppressed at high number density electrons. But you still need free electrons around to scatter off of. Those quadrupole moments have to scatter off of free electrons to create polarization. So you need to be in this sweet spot where there's low enough number density of electrons to allow free streaming, and yet there's still electrons around to scatter off of. So here's the visibility function versus conformal time here. So today is far off to the right. And at 200 megaparsecs and smaller, the mean free paths are very short. There's no quadrupole moments. At 400 megaparsecs and higher, there's quadrupole moments from free streaming, but there's very few electrons to scatter off of. So all of the polarization that isn't created in the reionized universe more recently, all the polarization that comes in at L greater than about 30 is generated in this window here, where the visibility function is significant. And there's this analytic treatment of polarization generation from Zaldariaga and Harari in 1995 that's really useful. And I take here a result from it. So the dominant source of quadrupoles actually comes from free streaming of gradients in the peculiar velocity. So here that there's this gradient of the peculiar velocity term, and then so you need time to free stream. So there's this delta A to vis term. How much conformal time do you have while the visibility function is significantly non-zero? So you can think of this as like a full width half max of the visibility function. So you need that free streaming to happen, and you need that happens over time. But you only have so much time while you still have scatterers around. So how is this impacted by changing h of z? Well, we have to focus on observables. We aren't not observing k, we're observing L. So if we rewrite that Zaldariaga and Harari expression, getting rid of k and replacing it with L, then we see that this combination here has a delta A to vis over A to naught. And if any of z is unchanged under our scaling, then this is a scaling invariant quantity. So we'd expect that this polarization generation would be invariant under BAO scaling. However, any of z is sensitive to h of z, as actually Zahn and Zaldariaga pointed out in a 2002 paper. Recombination is an out of equilibrium process, and so there's sensitivity to the expansion rate. If you're expanding more rapidly, it's going to be harder for electrons to find protons to combine with, and so as you expand more rapidly, at any given redshift, the number density of electrons is going to be larger than in a model where you're expanding more slowly. So here's a ratio on the left plot of number density of electrons compared to number density of the fiducial model, which is the standard model, as the density parameters are varied along the BAO scaling direction. And here, those numbers in the legend for the plot are values of NF. So as NF goes up, the number density of electrons at a given redshift goes up. The transition is smoothed out. So this delta A to vis over A to naught is actually increasing with N effective. So that destroys the scaling invariance of the polarization. And so delta A to vis A to naught, right, is now changing with scaling because of the sensitivity of recombination to the expansion rate. How do power spectra respond? Let's look at that as we vary parameters along the scaling direction. So on the left is the temperature power spectrum, on the right is the polarization power spectrum. These are actually multiplied by L times L plus 1 over 2 pi, even though they're not labeled as such. We see that here, a dominant effect is this effect of the free streaming decreasing the amplitude as N effective is increased. So that's why we see the power going down, and that's influencing, of course, both temperature and polarization. If we fit these AS, NS, and tau parameters to the Planck temperature power plus low L polarization, then we start to see our effect, right? So if AS and NS are adjusted to fit Planck data, right? Of course, we've now reduced the differences between all these models in the temperature power spectrum, and we're starting to see this effect, this recombination clock effect of boosting this low L power. We still have this, effects of the damping in the temperature power spectrum at high L, and we're still seeing damping at high L in polarization also. But at low L, where the damping is less, we're seeing the impact of this recombination clock effect, where the faster expansion rate has spread out recombination, boosting polarization power at large angular scales. So we can see this correlation of polarization power with this fractional width of the visibility function in our chains in all of these model spaces. And so we think that this is playing a very significant role, this recombination clock effect, in tightening up these constraints from temperature alone to what we get with polarization. Now, in the NF plus fluid plus helium case, it kind of stands out in that so that's this purple line here, extending to higher Hubble constant. There's having the fluid rather than the free streaming opens up this degeneracy direction with helium that does not get opened up as much with the free streaming case. And so what's happening here is we're actually going to fairly low values of helium in order to come out here to the high Hubble constant. So you can see that here in this plot, that getting out to this high values of the Hubble constant, you're coming down to low values of helium. So you might worry about that, right? Because there are measurements of helium and inferences of the primordial value of helium from them. Here's a compilation in a recent paper of these measurements, and they're all at higher values of helium than we get in this plot here. Here's roughly the 2 sigma bound from Aver et al. And if we put that in as a prior, we basically wouldn't get this. That purple curve wouldn't stick out into the beyond 70 like it was doing earlier. So that's basically why my answer at the moment is no. Of course, it's always conditional upon thinking of something else that could impact recombination, and is there some new idea to inject here that would open this up more? And that's always a possibility. But at this point, it's starting to look really complicated, and there's not any preference for it in the CMB data, and it's a challenge. It seems to be a challenging way to go using light relics. But it's highlighted for us the value of polarization, and so I just want to tell you briefly here in my last few minutes about SPT3G. So SPT is the South Pole Telescope. It's a telescope, not surprisingly, at the South Pole, the 10-meter telescope that has previously executed 2 surveys, SPT-SZ and SPT-Pole. And now we're on to the 3rd generation focal plane, SPT3G, started surveying in 2018. And with plans to survey for 5 years, we just a few months ago released our first power spectrum measurements. And this was done with half a season, with half a focal plane. We've since observed 2 complete seasons with complete focal planes. But even from that half a season and half a focal plane, we've gotten very competitive constraints on the power. So here's Planck as we're getting to smaller angular scales, the errors going up. Here's the ACT DR4 that was mentioned earlier. Oh, all right, you can't see my cursor. Anyway, you can see the colors here. Here's ACT DR4 in a kind of light purple. And SPT pole, previous survey in dark blue. And so with very small error bars here, comparable to the ACT DR4 ones, and also consistent with lambda CDM. This is a lambda CDM fit to SPT3G. Here's the residuals of that fit for EE, and also the residuals to that fit for TE. So the successes of the lambda CDM model on small scales, we see this as being well supported from this new data from SPT. We're working on converting this to constraints on light relics, and those results should be out soon. This will put yet, I think, more pressure on light relics as a solution to the Hubble constant problem. So, to summarize, we found BAO scaling to be a useful concept for analytic understanding of constraints in these model spaces. Well-known BAO scaling and variance breaking effects are important for constraints on light relics, photon diffusion, free streaming induced potential decay. Another effect, which is described by Zahn and Zaldariaga, but not previously emphasized in the context of the Hubble constant problem, is this recombination clock effect. The sensitivity of the recombination process to the absolute value of the expansion rate during recombination, and then the polarization sensitivity to those free electrons. So polarization, we found, we think because of this effect, severely constrains light relics, even when other freedom is introduced, even if we introduce helium and the free streaming fraction. Helium is itself constrained by observations of metal poor extragalactic H2 regions. So that's a thing to consider. I'm still not quite sure how to interpret those error bars, what modeling effects of these very complicated H2 regions may still be left out. Are these uncertainties underestimated? I don't know. Even so, things aren't looking promising for light relics, even if you open that up some. The EE and TE measurements coming from SPT3G will get better over the next few years and will provide another precision test of lambda CDM, which so far LCDM is passing. An analysis of the constraints on light relics is underway and will be out soon. I guess there's one other thing I didn't say that's written here, which is that this recombination clock effect may be important for constraining other early time solutions to the Hubble constant problem as well. Not that people aren't including it; it's automatically included, right, in the calculations people are doing. But in terms of understanding where the constraints are coming from, this is an important thing to include. So let me just say, since this is the last talk, well, first of all, I answered the question, right? Additional light relics is looking about as kludgy as my addition to this bridge, and perhaps is likely to toss you in the metaphorical river. And so that's the answer to the question for now. And let me just say thank you again to the organizers for managing to put together and bring us together for this very interesting conference. I've enjoyed it very much.
Thank you very much, Lloyd. And let's thank Lloyd. Thank you very much. Is there any question? Okay, Niayesh, please.
Let's see. Hey, can you hear me?
Yes, I can.
Hi, Lloyd. How are you?
Oh, hi, Nash.
So I have a question for you. So Francis had worked on this idea of self-interacting neutrinos, which I think is kind of in a similar vein as this fluid light relics. So what is the latest on that? Because I think he was saying that it actually works, but then I have some recollection that there were some problems with it more recently.
Yeah. So definitely. So the fluid component here is just the limit, right, of strongly interacting, and there are certainly some interesting results obtained where you vary the strength of that interaction, right, and going back to work that Francis Jan did with Chris Sigurdsson, and where the neutrinos transitioning from tightly coupled to free streaming, doing that transition when modes that contribute to L equals 2000 are entering the horizon, that opened up a shift in parameters that gave you this this multimodal distribution where you had this mode that did have a higher Hubble constant, right? And so that's been an interesting line of work for a while. They also recently, with a graduate student at Princeton, Kreisch, looked at adding in giving masses to these neutrinos, and found that you could accommodate masses of 0.4 eV and get a Hubble constant of 70, and that was all pretty exciting. But that was before adding in the polarization data, and that's not happy what happens with the polarization data included. So anyway, that's some of the history there. Yeah.
Okay, wonderful. Thank you.
Thank you, Niayesh. Is there any other question? Okay, if there is no more question, let's thank all the speakers from this session, Lloyd and Levon, and all the speakers today, and all the speakers in the whole conference. Thank you very much. And okay, if you all give me 4 minutes, let me say something. Our idea was to have different viewpoints on the tensions, different viewpoints on, to organize this conference, to gather different people with different viewpoints. And I'm not sure if you read the emails and everything. And I have to say that we would like to thank all the participants for joining us, and all the speakers for accepting our invitation. It was impossible without you to organize this conference. I would like to thank the scientific organizing committee. I can name all of them if you like. Okay, we thank Niayesh, Ravi, Dragan, Roya, Yashar, Arman, Shant, and Marzieh, and the local organizing committee. I would like to thank Marzieh and Shant for, it was not me actually, it was them, to be honest, and we did all of things together. And my special thanks goes to Puyan and Mohammad Sadek, especially Puyan. Without him, we couldn't make it. If you see everything is smooth, it's because of Puyan. So please thank all the organizers and Puyan and everybody, please. So that, and we hope, thank you very much, and we hope we can organize it, because this one was the third meeting on this Tehran meeting series. So we hope we can have the fourth one and not virtually, and we hope we can see all of you in Iran. Thank you very much, and bye-bye. Thank you very much. And yes, Shant is the one. Okay, so if you want to, I can give you access to the microphone. Shant, please.
Okay, so if everybody agrees in behalf of the scientific committee, I want to say that Nima is the backbone of our committee. He's the doyen of the committee, and let's thank Nima very much. Thank you, Nima.
Thank you very much, Shant. Thank you very much. Thank you very much. So if there is nothing more, okay, goodbye, and I hope to see you in Iran. Thank you very much. Bye-bye. Puyan, can you hear me?
Yeah, I'm here.
خب ببندیم در اینجا. ما داریم الان روی یوتیوبیم یا نیستیم؟
هستیم ولی خب
هستیم. ما we should thank all the audience who watched us live. Okay, I have a call, so let me just. Here's Sohrab. Salam Sohrab. پویان ما همه چی تمومه؟
همه چیز تمومه.
یوتیوبمون رو میبندیم؟
یوتیوب رو بستیم.